Hello, this is Warren Redlich. Thank you for watching. I'm here with James Douma. Am I pronouncing Douma right?
It's Douma, but don't worry about it.
Okay, so James Douma. James Douma is, in my opinion, an expert on artificial intelligence and probably a lot of other things I'm not sure about. James, could you give everyone a little bit of your background?
Wow, where do I start with that? So I'm a self-taught lifelong engineer. I've worked in a lot of different industries. I've been doing AI-related stuff since, I don't know, the 80s or something like that. The most of my career, I've been designing various kinds of hardware systems. I'm a big software dork too. And artificial intelligence was my first love, but you couldn't make a living at it when I got out of school. So I did a lot of other things. And now that I don't have to work for money and can do whatever I want, I spend all my time doing AI. I mean, all the time that I'm not like vacuuming the floor or doing all the other stuff people do to live.
Cool.
So
okay.
Anyway, my background on Tesla, that might be of interest to people. So I was spending full time working on trying to understand algorithms that could learn sometime starting in 2007. I was doing it more time. I was working with a group of people who were investigating various approaches to developing. I had this term I called the algorithm with a capital A, which was it was a thing that seemed to me to be the one thing that we were really missing, or one thing that if we had it, it would really change our ability to build machines that could be our agents in the world. And that was the ability to train sophisticated algorithms from data, like build systems that could learn on their own. And so starting in 2007, I started working on this full time. And around 2013 or so, I became aware of ImageNet results and immediately realized, having spent the previous 6 years trying to tackle a similar problem on my own, that somebody else had found the answer, and this was it. So basically, since 2013, I've spent all my time trying to understand the implications of the deep learning revolution. So when I found out that Tesla was doing sophisticated control systems for cars, I became really interested in what they were doing. I went out and bought myself a Tesla Model S as soon as they had AP1 out, and spent a lot of time trying to understand how that was working, and just sort of driving it around, exploring its capabilities, and doing internet research, trying to understand how they were accomplishing what they were accomplishing with it. When AP2 came out, I went and got an AP2 car to do the upgrade, and continued that. At some point along this chain, I became aware that there were people who were hacking the cars and getting the code out. So I begged to get copies of this stuff, and I worked with some other people to build tools to try to understand, kind of from the inside, what was getting engineered into these systems. So the last several years, I've spent a bunch of time trying to match what I see, or what I can see from code that I get from other people, and what the cars seems to be capable of doing in the real world. So that's sort of the essence of my background on this topic.
Okay, just to be clear, do you have FSD Beta?
I do not.
Okay, so do you have a Tesla? Do you have FSD?
I have bought FSD 6 times now.
Okay.
I've got a couple of Teslas right now. I have ridden in FSD Beta cars. Like, I know people who have it, so I've been privileged to observe it in the wild. But I do not have it myself.
Okay, so let's just talk about that for a second. What differences, if any, do you notice between the FSD in your car and the FSD Beta that you've ridden in?
Well, I mean, anybody who's got FSD in their car, FSD in the cars today, there's no FSD in the FSD that you get if you don't have FSD Beta. What you have is a set of features that are essentially add-ons to autopilot that make it a more capable level 2 system, but they do not at all make it a level 3 or a level 4 system. I mean, aspirationally, maybe they eventually get there, but they don't have they're not feature complete for doing that. That is, the FSD includes features like nav on autopilot, right? So nav on autopilot, if you have that feature and you use it, it's capable of, if you get on a limited access highway, it can it can take you from like an on-ramp to an off-ramp, including all the interchanges. At least aspirationally, it can do that. It's not perfect at doing that today, but it'll do lane changes and it will deal with traffic on freeways pretty intelligently. Now, I mean, the bar keeps coming up, but its ability to interact with other drivers, to make lane changes, to avoid people who are doing stupid things or acting, basically if somebody changes lanes into you from a blind spot, and you don't notice them, autopilot will get out of the way, right? It will take that intervention itself. So Nav on Autopilot has a whole stack of these sort of incremental features that add convenience features to the core level 2 capabilities of autopilot, but which do not attempt to solve the whole problem. So to solve the whole problem of being able to go from any point in the world to any other point in the world, there are lots of corner cases and lots of special rules that you need to tack on to the way that Tesla is doing autopilot now. So just broadly speaking, Tesla uses neural networks and they use quite sophisticated artificial intelligence techniques to deal with perception in the world. But for the most part right now, they are taking those perceptions and then they are hand coding a set of heuristics, which are basically rules for like, in this situation, do this. And that whole stack ends up sort of creating the set of things that autopilot can do, or FSD Beta can do at this point in time. FSD Beta, the version of the code that I've seen, the version of the neural networks that I've seen is clearly designed to work inside this environment where there are humans writing a bunch of rules, but the network itself, the neural networks themselves are producing these relatively highly abstracted perceptions of the world. For instance, the neural network doesn't have to be restricted to, there is a car of this kind at this position relative to you, right? It can say stuff like, there are no cars about to merge in front of you, or there is a car about to merge in front of you, or, we do not want to be at this location, this position in the lane right now. It's once upon a time, autopilot was basically on rails. It drove right down the center of the lane. And now autopilot sort of it takes a more holistic view of the situation that the vehicle is in and decides where in the lane it ought to be. That's how it can move over to avoid a cyclist or a motorcycle when it comes on. So when they do that, they don't have to heuristically, with a set of human written rules, sort of say, oh, here's a motorcycle and it's at this location. And let me look in my table to see how much space I should give a motorcycle. Okay, move the car to the left 4 inches. Instead, what they can do is they can just ask a neural network, given the whole set of vehicles around you and the stuff that's coming up, where should I be in the lane? And the neural network will have a proposal, and then they can decide to go to that proposal given heuristic constraints that they might choose to apply. So as the neural networks get better, the way they describe the environment, the information that they pass to the people who are writing the rules for how to drive the car, are more sort of human-like. They're higher level abstractions. Instead of having to be simple, concrete descriptions of specific physical things in the world, you can ask more general questions about the environment. Like, in this situation, what would you recommend should be the easiest path forward? And the neural network can look at the available space. It can look at where the other cars are. It can look at whether there's construction cones and all that kind of stuff. And it can say, this is the proposed, path of least resistance through this environment.
Well, let me try to bring this back. And just real quick, I want to remind my followers, please support this channel on Patreon. Patreon supporters get early access to some videos, bonus content. I forgot to give people a chance to submit questions on Patreon. So one of the thoughts that I had to try to break down what FSD really does is to start with this. What are the major inputs to FSD? And my impression, I think the major input is cameras, that there's 8 cameras and each camera is transmitting pixels. Maybe it's 1024 by 768, maybe it's 1280 by 7, whatever. There's some 1920 by 10.
1280 by 960 3-color HDR cameras.
And there's 8 of them.
There are 8 cameras. 7 of them are different than the 8th one. The backup camera actually has a different color space. The backup camera, I suspect the reason that the backup camera has a natural color space, a conventional RGB color space, and I suspect that the original idea with that was that people are going to look at it for backing up, and you want the bushes to be green and the concrete to be gray, and you want everything to look the right color. So they picked a conventional color space. But the other cameras on the car, they were originally intended to only be used for driving related functions. And so they picked a color space and a dynamic range for those cameras and a resolution for those cameras, which is optimized for the task of driving. It has good resolution and dynamic range for the information which is most useful for driving, and it doesn't concern itself very much with whether, if a human being were to look at an image from this camera, does it look natural?
Okay. So I want to try to understand how FSD works. And what I understand is there's this chip in the car, or there's two chips in the car that are known as inference chips, which I'm going to ask you about inference later in this conversation. But there's a lot of pixels coming in. There's what I would see as a black box, and then something comes out the other side. There has been in the past, or there currently is maybe in your car, radar is another input. Maybe sonar is an input. Are there other inputs besides the cameras, radar, and sonar that go into the FSD inference chip that it processes to get to its outputs, which we'll talk about shortly?
So that changes over time. And where you draw the boundary of the black box changes the answer to that question, and when in time you ask that question, because it's something that is worth keeping in mind about both autopilot and FSD is that there isn't really a definition of what it is, because the definition evolves. Having watched the evolution of the system over time, I can tell you they are constantly doing a large number of experiments. There's a ton of stuff in there at any given point in time, which is not driving the car. It is experiments that the AP team are pushing out to the field to try something to resolve. They're constantly trying to add new functions. And when they add these new functions, they try things. They don't sit down. They're not doing the Boeing approach where, you try to prove the thing works in simulation and then you just write it and push it. They push test versions out to the fleet. They see what they do for different approaches to dealing with certain things, and then they refine the approaches that do work, and then they down select and add the feature at some point in the future. So what autopilot is at any particular point in time is this moving target. Like literally every time they push an update out, it's different. They've added some features, they've added some experimental stuff, they've pruned off some things that weren't working as well, they've refined some other techniques. And at any particular point in time, they may be pushing many different versions to many different vehicles. So they're running a lot of experiments in parallel all the time. And I think it's probably better to think of this as a giant work in progress and not a finished product. I mean, we're all driving, some intermediate revision of something which eventually is going to be better, and which probably doesn't have a stopping point, right? I don't think even after the cars are out driving themselves around and you can do robotaxis, there'll be things it can't do. It won't be good at snow. It won't be good. Maybe it can't handle a situation where a camera is out. Maybe it's not as good at facing straight into the sun. Maybe there are dynamic traffic situations it's not as good at. And they're just going to keep adding these features. And I think it's going to continue to be a work in progress for decades, right? And as more people drive it and Tesla pours more resources into it, it's, the effort's going to expand. We're on hardware 3 now. There will be a hardware 4, then there'll be a hardware 5, because the silicon is going to keep getting better. The software is going to keep getting better. I think the one thing I would say they probably won't change is I think they probably won't change. They're reducing the number of sensors. I think they'll probably go down on the number of sensors. They might go to higher resolution cameras. And I had thought at one point that maybe they would go to multispectral cameras or thermal cameras. There's a lot of other sensors besides like sonar, radar, and lidar and cameras that you could potentially throw in there. And a lot of them are inexpensive. They haven't been looked at very closely, but it does seem at this point like they're going to double down on cameras, and they're just going to keep pushing that. And to be honest, that what you could achieve with the sensors that they have now, I mean, they're very, very far away from hitting the limits of what they can do with the 7 cameras they have in the car. They could keep just pouring resources into compute and resources into software and training for 10 years, maybe, before the sensors are going to start being the limitation on what they can do.
Okay, really quick, because somebody asked this. I'm going to speak in Japanese and ask you to respond. Dauma-san, yoroshiku onegai shimasu. O genki desu ka?
Genki desu. Arigatou gozaimashita.
Okay, so James and I both have some experience speaking Japanese, and someone in the chat asked us to speak Japanese. Actually, a couple of Japanese-related comments in the chat. Sure. So my impression is Elon said we're ditching radar. So it seems to me the primary input to the FSD chipset is the 8 cameras and not much else. Maybe the sonar is a significant input, but my impression is they're trying to do this on pretty much vision only for a while. Does that sound right?
So right now there's there's a perception stack.
Yes.
So let me take a step back from that. So driving is perception, planning, and then action on top of that. The perception right now is totally dominated by the cameras. Planning is kind of a 50-50 split right now. They've got neural networks that are doing some of that, but a huge fraction of that is getting written heuristically. And action is completely heuristic. That's all handwritten code.
Let me just explain that to people, because I think you speak at a higher level, and I think I understand what you're saying. So,
okay.
Let me try to take this away. I think this is going. The first step for the FSD chip and software is to see the world, perception, identify objects. I'm not sure where this fits in there, but it's like identify where it thinks objects might move. Right? Is that still in perception?
Understand the situation.
Right. But
that's perception.
So I've seen Elon talk about probability vectors. I saw Jim Keller with his interview with Lex Friedman talk about, ballistic probabilities. My sense of it is the first step for the FSD chipset and software is identify objects that are on the cameras, and possibly things that aren't on the cameras, but things that you were there before and they're occluded, but they're supposed to be there. But identify objects and then assign ballistic probability vectors to them. I think, for example, stop sign shouldn't move. The ballistic probability around stop sign is it doesn't move.
Ideally, yeah.
Car coming from the right, it's currently moving at this velocity. Ballistic probability, it's probably going to keep moving in the direction it's moving. And there may be some variability to where it thinks that object might move, but is that still in the perception part of the stack, that you're identifying objects and you're predicting where they're going to move?
Yeah, that's perception.
Is there something else in the perception stack?
I guess depending on how you talk about it, you could imagine different things. But I mean, just super broadly, perception is tasked with understanding what's the current situation, and that includes not just the current positions, but the future probabilistic trajectories of everything in your environment, including yourself.
Right.
Okay. Planning is, this is my situation. This is my goal. What do I want to do to achieve my goal given this situation? So perception looks at the world, tries to provide the current situation. Planning tries to take that situation and the objective that you have, that you've been given by your user, and determine what the best course of actions is. And then the third stage is doing those actions.
Right.
So,
well, let me take that on. So I'll just give you my rundown of what I think it's doing, and you can tell me if I've got it wrong or if I'm missing some details. So the first part was observing objects, predicting probability vectors. For me, the planning part is, okay, we're trying to get to this point. Let's minimize the probability we hit something, right? We still want to get there. We want to try to maintain our speed. There's some modification, because you can minimize the probability of hitting anything by not moving. So you have to have some part of the objective function of getting to where you're going, right? But a large part
if
of
your goal is to get somewhere, then not moving is not an option.
Right. So the objective function has to be, and I'm sorry for those who aren't I have a little bit of a math background, haven't used it much in the last 30 years, but to me, there's an objective function. It's like, get to this place and don't hit anything. And there has to be some non-zero probability of hitting something in order to be able to get where you're going. I mean, you're trying to minimize the probability. You're trying to get where you're going. I mean, does that sound like the rough idea? I think we're going to leave out, I roughly agree with you that the execution of the plan is probably still heuristics. So I think I've seen them talk about, maybe it was you, maybe it was Andrej Karpathy, that ultimately the machine learning is going to eat even the execution of the actions.
Yeah.
But for now, I think my impression is that planning the path is now pretty much fully, the machine learning is planning the path. Do you think that there's still some heuristics?
No, it's planning. There are aspects of planning which are using machine learning to, for instance, the path effect. There's a, if you've watched the FSD videos, you'll notice that there's this little line that comes out of the front of the car, and sometimes it angles around other cars, or sometimes it turns corners and whatnot. So that's that line is output by a neural network. It's coming out of a neural network because in order to do that line, in order to be able to make that line, you have to take into account a whole lot of things that it's very difficult to write all the rules for. Is there a bus? Is there a biker? What angle is this street? Is there a stop line? What stage is the light? Is someone running the light? Just on and on and on. What's the appropriate path? If you come up behind a vehicle that's stopped in your lane, is that a bus pulling over to drop people off? Should I wait? Is it safe for me to change lanes to go around it? Or, do I go around it? If I go around it, do I start my lane change 100 feet back? Do I go up behind the bus, stop, wait, and then do, there are a lot of things that go into figuring out what the shape of that line ought to be. And they've been producing that line with the neural network now for 18 months or 2 years. I mean, they started much earlier than I expected them to. I was surprised when the neural network started outputting that path vector. So now that path vector, it's an input to planning. The planning is still getting done but that vector is a component of planning that makes the job of the person writing the code that does the planning a lot simpler. So right now, you don't feed a Google map into the planning network, and then it figures out what your route is, right? The planning thing, it takes a Google map and it executes an A-star algorithm or something like that to sort of figure out, to get to my destination, what are the turns I want to take? What roads do I want to drive on? And then the planning network that's actually driving the car, it's just taking a tiny little bit of that at any given point in time, right? It's looking at for the next, what's the next segment of my drive? How far am I going before I do a turn?
So
right?
the FSD might be looking 100 yards ahead. It's not looking 5 miles ahead.
Yes.
Okay.
I mean, well, in a sense, the FSD, it's interesting. It's easy to get confused about what part is the AI. FSD is the whole program, right? Yeah. Which includes the call to the Google Maps.
Sorry, the neural network.
And actually, I kind of, right now, I like to use the term autopilot as opposed to FSD.
Okay, but the neural network is maybe looking 100 yards ahead, but there's other code that's yes. doing the long-term planning of this is the route we're going to take to get to our destination.
At this point in time, to a first approximation, you could say the neural network is only concerning itself with the volume of space which can be directly perceived, right? So if you can see 100 feet down the road, if you can see 200 feet down the road, the neural network is taking that into account. It is not taking into account anything that it can't see, for sure. Well,
it may have seen an object
from temporary occlusions.
It may have seen an object go behind something and figure that thing might come out the other side and to be aware of it. Okay, right. So the input is largely pixels coming from the cameras, and the output is largely a path. Are there other bits of the output from FSD from the machine learning part of FSD or autopilot?
Okay, the output is not a path. The output is thousands of discrete. I think it's, well, so there are approximately 1,000 tensors that come out of this. So each individual tensor is a block of data that represents some aspect of the world that the neural network has been tasked with providing an evaluation of. So for instance, there's one of the neural networks produces a tensor for the front main camera, which is what is my drivable space, right? So there's a drivable space tensor, and what the drivable space tensor does is, it's a field that basically maps onto the field of it. It's a two-dimensional set of numbers that describes the likelihood that you can drive on any particular piece of ground in front of the car.
Okay.
Right. So, for instance, a K barrier would not be part of it. The asphalt you're driving on would definitely be part of it, and then the shoulder might or might not, and then the field adjacent to the road, or driveways that are adjacent. All of these have different representations in the drivable space map. So the drivable space map is just one output from the network. Now, that drivable space map isn't necessarily being used to generate the path vector, but it is useful to the guys writing the heuristics that control the vehicle, because there are a lot of rules that they might want to write to add to that path vector. Like, for instance, if I think this car is about to pull in front of me, slow down to give him time to, if you're coming to an intersection and a driver pulls up and they're going to turn right, and they're going to turn right into your lane, any human being approaching that intersection, you watch that driver, because he might not see you, and he might turn in front of you, and that creates a challenge for you. So there are people writing heuristics at this point in time to basically evaluate that situation. So the neural network can help by providing a probable path for that. The neural network can also do a thing like, did the driver look at me? Can I see his face? Right? That the attention thing that you do, and that's a thing a neural network can actually do pretty well. But to try to infer the intent of a vehicle based on its motion and position and the other vehicles around, and that sort of thing.
But when I say output, if there's 1,000 tensors, my image is you have the FSD chipset, and a bunch of pixels are coming into the FSD chipset, and something's coming out of the FSD chipset and going to the machine that whatever software or hardware drives the car, right? So when you say there's 1,000 tensors,
FSD drives the car. The output of the FSD is the frequency and amplitude of the current that or the voltage that you're going to apply to the steering motor. Like, at the end of the day, that's
but I mean, there's these two chips that are known as the inference chips. I'm trying to narrow right in on the inference chips. That there's, if I'm correct, there's pixels coming into the FSD inference chips, and there's some sort of data coming out of the inference chips. There's these two chips, right? They're a sort of supposed to be redundant chips, right? That were displayed at autonomy day.
There's two SOCs in what Tesla calls the FSD self-driving computer. So
when you describe
a single board, it has two SOC. A SOC is a system on chip. So it's a 14 nanometer TSMC, or it's a Samsung silicon, but the SOC contains the overwhelming majority of the simple computational. When I say simple, not to suggest it's simple, but for instance, there's a power supply and it has silicon, which is separate. And there is silicon in the FSD computer, which is not in one of the SOC chips. But there are these two redundant SOC chips and each SOC has 12 ARM cores. It has a sizable GPU. It has two of the neural network matrix multiplier units, and it's got a ton of other stuff. It has a vision pre-processing engine. It has it has encryption hardware. It has there's a bunch of little specific processing units that go in there, but by and large, the overwhelming majority of the computation in the system is happening on one of these two redundant SOC chips. But they're redundant kind of in the ways that the two engines on an airliner are redundant, right? That is to say, if you lose one, you can still operate, but they're not mirror identical copies doing exactly the same thing.
I'm just trying to get a grip on. To me, the cameras are not part of the system on a chip, and the accelerator and the brake pedal and the steering wheel are not part of the system on a chip. So in the car, the data is coming in from the cameras, and something is coming out of the system on a chip to go to the steering wheel, the brake pedal, and the accelerator pedal. And to me, or I don't know if they go directly to that or if it's drive-by-wire or whatever, however that's working.
It's a command over a CAN bus that interfaces to a controller on the motor for the steering system. Yeah.
So I'm just trying to get a feel for this is my monkey brain trying to get a hold of this neural network process, because you mentioned the matrix multipliers, right? And we're going to head to Dojo or the training part in a minute, but it's taking in data from the cameras, and it's somewhere along the way instructions are coming out. Here's where we're going to go. So somewhere in this process, you've got video in, it perceives the world. There's some kind of path planning, and instructions go out. Okay, here's where we're going to go. Am I in the ballpark of correct with what this is doing?
Yeah, no, that's right. The camera feeds come straight in. Right now it talks to the radar over the CAN bus, and there's a sonar controller somewhere in the system, and it talks to sonar controller over the CAN bus. So a CAN bus is kind of like a little Ethernet network inside the car. It's got CAN buses that it uses for talking to other, smart systems elsewhere in the vehicle. But yeah, it's overwhelmingly pixels coming in and the system deciding based on pixels what it's going to do. But the process for decision is, you pre-process the video, you have to get it into a format where a neural network can digest it easily. Then you feed these cameras into a whole array of neural networks. Right now there's a bunch of different neural networks. At any given point in time, there's some neural networks that are driving the car. There's some that are experimental. There's some that are just used for like looking at the world and gathering data for Tesla to do future training on and that sort of thing. So all of these networks process these images from the cameras, and sometimes you have multiple independent networks associated with a particular camera. Each of these networks outputs a large number of pieces of information about what it sees that they've been trained to do. And so you've got these thousands of blocks of information that come out, and those are going into code that a human being wrote, right, to make decisions about driving, right? And then the output of that is going to be a set of instructions that go to these controllers that turn the wheel and press the brakes and so on.
I just thought you'd appreciate that. Rexy the Hound said, "This is like watching a Boeing engineer explain how a 747 works to a caveman." I'm pretty sure I'm the caveman in this story.
Your audience is very appreciative of your efforts, it seems.
I'm entertained. So,
no, I like this format where I'm not necessarily good at trying to figure out how to frame these things for people. So, like, if I can convey the information to you, then some people in the audience will get it, right?
Yeah.
So that's good.
Well, we're trying. So one of the things that I think is a really important feature of what's going on in self-drive in Tesla's cars is object identification.
Yeah, that's super important.
So, and hopefully this noise will stop in the background, but the pixels come in and the car is trying to identify objects. So it sees a stop sign, it sees a traffic light, it sees a pedestrian. Do you have a sense of how many different categories of objects Tesla uses to, in sort of its identification? How does it build a library of objects to identify? Dog, cat, bird, squirrel, human, car with bicycle on it. There's a whole. I remember there was this whole thing where Andrej Karpathy was talking about car with bicycle on it. Recognize that the bicycle it's not really a bicycle anymore. Do you think they build up a vocabulary for the software to understand what objects are?
Yeah. They build a big. So the data they use for training, it's in the business we call it the training corpus, right? It's this set of data that you're going to use. Corpus, C-O-R-P-U-S,
I know.
like a corpus of text. Okay. That training corpus, it will include it will include explicit examples of things that you think are important to identify explicitly, and it will include groups of things that you think are significant in some way, but which you don't necessarily need to explicitly identify. So, for instance, a stop sign you want to explicitly identify, and you may want to categorize it. In fact, Andre's he's talked at length about stop signs, right?
Stop sign on an arm.
A lot of different kinds of stop signs in the world,
right?
And they're super context. The stop sign on the school bus is a stop sign,
yes.
and but it. And then there's, stop signs on, some gates that go up and down, or gates that open. And so you have all these state dependent stop signs.
Did you see recently there was a stop sign on a billboard and the Tesla stopped because there was a billboard off to the side of the road that had a big stop sign on it? Yep. And it got confused because it saw a stop sign that wasn't really a stop sign.
It's a context dependent thing, right? It's I remember when the stop sign detection at first happened, and if you saw a school bus with a stop sign on it, it was a problem, right? I mean, so we'll just take the stop sign, the stop sign on the school bus thing. Okay, so my neural network has been told to identify bus, right? Maybe it doesn't have a category for school bus yet. And it's been taught to identify stop signs. So at some point, do I want to create a special category for, stop sign on a bus? And so you could imagine that there are different ways to go at this problem. Like, you could have a human being say, oh, is there, here's a stop sign, here's a bus. And the human written code, is this a stop sign on a bus? And then deal with it that way. Or you could say, I'm going to collect a corpus of stop sign on a school bus things, and I'm going to recognize that as a separate category, and I'm going to deal with it that way, right? So those are both legitimate approaches. And depending on the accuracy and how difficult you think it is to write this piece of code, how buggy it will be, how hard it is to integrate it, you might choose one path or the other. In fact, looking at Tesla's evolution, it's frequently been the case that they have handwritten a solution to something that they needed to solve to do what they want to do today. And then later, more and more of it gets absorbed by the neural network. So maybe initially you've got the stop sign and the school bus, and you already have the school bus thing working in your neural network, and you already have the stop sign thing working. And so initially, a human writes is this a stop sign on a school bus thing? And what do I do if it is? Sort of thing. And then a little farther down the road, your engineers might say, this piece of code, it's not working so great. What we really need is a stop sign on a school bus category that the neural network detects directly and tells us. So then they go, okay, we need a bunch of pictures of school buses that have stop signs on them. So then you build you take a bunch of pictures of school bus stop signs. You can create a latent representation of this, which is just, it's basically this mathematical representation of what is happening at a particular stage in the neural network, which is very strongly correlates with when the neural network is seeing a stop sign on a bus. You push that out to the fleet and you say, you can tell every single car out there in the fleet, all those millions of cars, you see one of these, take a snapshot, send it to me, right? And 10 days later, they've got 100,000 pictures. So they have some people go through those, say, this one's good, that one's bad. You stick those in the training corpus and you say, hey, when you see this, give me the stop sign on the school bus flag, and blam, you've just added a thing. In 10 days, you can go from an engineer deciding we need this in order to improve the performance, to go out to the fleet, get the data, add it to the training corpus, turn the crank on, this is Carpathy's data engine, right? And now your neural network is telling you with some significant level of accuracy, when that phenomenon is occurring in the world, when I have a stop, and you could go further. You could say stopped school bus with the stop sign extended, or is the stop sign extended or not? So now you have a state variable. And over time, what happens is you see the neural networks, they accumulate more and more of these variables, right? And then occasionally you see a thing where they consolidate a bunch of them down into a single variable that they want, which better captures the overall situation. And then you see the neural networks change and they get rid of all those ones they had before, right? Yep. So things expand, they add more variables, then you get consolidation, and then they expand again. But the general trend is that you see more neural networks and they get bigger and there are more outputs.
Okay, so we talked about, I was heading somewhere with this, which I for those who don't know, I sent James an outline. I don't know if I was clear that this was going to follow a path.
James didn't get, so we're flying by the seat of our pants.
No, this I sent you before, and you said that you didn't need to prep for it.
Okay. That thing.
So we talked about object identification and probability vectors a little bit. That it's trying to figure out where something might go, or hopefully that it's not. If it's a stop sign, it's not moving. One of the conversations I've been having with a lot of people is, how do you measure how well it's doing? And I think there are objective things you can look for, and there are subjective things that you can look for. So in my mind, an intervention, when a human hits the brakes, that's the human saying the car did something wrong, but the human could be wrong, right?
Mm-hmm.
The human steers, the human might not have seen something the car sees. It's the human's and like you might have hit the brake, but I might not have hit the brake because we have different reactions to what we see on the road. You and I might drive differently from each other. So there's a subjectivity to human input. Objective input would be something like what Andrei Karpathy described in the Robot Brain podcast, flicker. It sees a stop sign, and then the next frame, it thinks it's not a stop sign. It thinks it's a yield sign. And then it flickers again, and it thinks it's a stop sign, and then yield sign, and finally it settles on stop sign. So that's an objective sign it's not identifying well, right? Or it could identify that object better. Another objective sign would be, I predicted that thing wouldn't move, and it moved. Or I predicted that thing would move with this probability vector, and it moved to a spot that was either completely outside of where I predicted it would move, or it was a low probability move. So those are two examples of things that I think are things you can objectively measure how well it's doing. First of all, do those make sense as things that you could objectively measure and then say, gee, we had a lot less flicker in this drive. And things moved within the vector that we anticipated. So it seems to be doing better. If we're seeing a lot of flicker, if we're seeing objects not moving where we predicted, then we're seeing it worse. Does that seem like some pretty good measures Tesla could be using to evaluate how well is this version of FSD working?
Yeah, sure. I mean, so it's nice when the neural network is not just telling you what it's seeing, but it's also telling you the confidence with which it thinks it's seeing stuff. And of course, ideal in the best of all possible worlds, everything it tells you with high confidence, and that confidence is well placed. You know, when you go back and you test it, when you test the neural network, so they'll do regression tests on these neural networks. You know, they got this whole giant suite of canned phenomena that they want to test, and they know what the results should be. So they train a neural network, they regression test it against all these canned scenarios that they have. And if the network is giving them higher confidence of the correct answer, right, then you're getting closer to the world that you want. But of course, this not just doing regression tests on your canned capture.
Just real quick, I think for the audience, I know what a regression test is, but could you explain to the audience what a regression test is?
A regression test, when you're building a piece of software and you want a particular output, one of the things that you can do is you can say, well, I know for this set of circumstances, I should get these outputs. In the future, if you change that code, you still want to get the answers that you got on the previous code. So you have this library of tests which are where you know what the right answer is for the test. So when you make a modification to the code just to check and make sure you haven't broken anything, you run the code against all these tests that you have in the can. Those are called regression tests.
Okay. So by regression test, you don't mean statistical regression. You mean you're making sure it's not regressing. It's doing stuff as well as it did before, and it's not getting worse on the things that it already did well. Okay. So I didn't know what regression tests were. Okay, so, well, I guess I was trying to figure out what else do you think they measure besides object identification, accuracy and consistency, and probability vector predictions? What are some other big things that might be objectively measured?
What might not? Yeah, that's a very large space of.
No, but what would be important for them to measure to see how well is it performing?
So there's
well, let me take a step back for a second.
It's a stack of functionality, right? At the end of the day, what you want is you want the user to get in the car, tell it to go from A to B, and for it to get there, and for there to be no interventions, and also not trip a lot of other flags. You don't want any. If the car ever had to brake hard, you want to evaluate. Well, did it have to brake hard because it made a poor judgment? Or did it have to brake hard because of some unforeseeable phenomena? Or, is the steering wheel wobbling back and forth, left and right? And then if you see a lot of variance in the output of things, like it's accelerating, decelerating, accelerating, decelerating, as opposed to holding, you want to try to understand what's stimulating that behavior, right? And if it was appropriate or not. I mean, if you see the steering wheel regularly wobbling a lot on a lot of different cars, it's probably not because the circumstance is dictating it. It's probably because there's something wrong in the algorithm, right? So there are any number of sort of little heuristic rules that you could come up with where you observe the cars in the real world and you use that as an evaluation criteria to help you decide if at the top level the software is working well. But of course, as you come down the stack, there are lots of small things also. I mean, it can be the nature of, for instance, one of the things that the neural network makes a determination of when you approach an intersection, if you live in a big city, it's pretty common to come to an intersection where you have a bunch of different lights, and the lights are relevant to different drivers. There's a left turn light, maybe there's a right turn light. There might be different lights for different lanes. So the neural network has to figure out which of those lights is the light that applies to you. You come to the intersection, it sees 3 traffic lights, and it needs to understand which one of those is the one that's relevant to you. So say you're the engineer who's tasked with getting this function to work really well, right? And you're not sure how well it's working in the world, and you've already gone through shadow mode, and because the first thing that you do is you write this function, you push it out in shadow mode, and then you might have some tests on the vehicle behavior that you would look. For instance, when it's sitting in shadow mode and it comes up to an intersection, you might go through this phase where you say, if shadow mode predicted that this was the light that was relevant to me, and the light was red, but the driver drove through the intersection, I might be wrong, and I might want to look at those. So let's capture all those events so that we can take a look at them, right? So you might go through that phase. Then later on, when it gets good enough, maybe now you're controlling the car, maybe you're not controlling the car. But you can write a heuristic to evaluate how well that particular aspect of this function is doing. For instance, did I come up to an intersection, see the light that was relevant for me, see that it was green, decide to grow, and then the driver had a panic stop, right? Because that might be a sign that I was wrong, and I need to look at that. So I can bet you that particular rule I just described, that's in the system, right? Because those are events they definitely want to catch.
Yeah.
So there will be a whole laundry list of those kinds of things in the system, which are, I kind of describe them as a code harness. Right now, you've got this horse, you're riding it, and you mostly trust it, right? But you don't completely give up controls. You have some framework that you let it operate inside of. And especially when you're not, for aspects of its behavior that you're not certain about, you keep a pretty tight rein on the range of things that you allow it to do to prevent a catastrophic outcome. And then as your confidence grows and it's demonstrated that it can handle a wider range of circumstances with better and better outcomes, then you can gradually loosen up those blinders that you've put on the thing. So when you ask me, well, like, what's a good candidate for that? Like, I could probably all day long, we could stand here and we could come up with, oh yeah, if autopilot decided to do this and then it saw this other behavior, that's a sign something could be wrong. And you capture those events. So there are lots of different kinds of triggers that you can have. But the one that Andre described, where essentially you see a stop sign, then you don't. You see one that you don't. Well, we know in the real world that stop signs are persistent. Right?
Yes.
They don't exist and not exist and not. So we're taking a human intuition that generally, if you see a stop sign, you should keep seeing it until you pass it. We're taking that human intuition and we're writing a rule and we're applying that filter to what the vehicle is reporting back to us to understand, does it make sense given our human understanding of how this phenomena should be in the world? And there's just a vast number of those that you could write, and there are probably a very large number of those rules operating in the car in all the cars right now.
Is getting the traffic light wrong really just a subset of object identification, or no, I knew it was a traffic light, I just didn't know which one was important? So it's sort of like, well, I guess I was going to say, when I talked about object identification and sort of like a library of objects and then probability vectors, I guess another thing that we want the car to do is like assign attributes to objects, right? So, and you see a traffic light, maybe it's not I'm identifying a red light, I'm identifying a green light, I'm identifying a traffic light, and I'm identifying an attribute. It's green, it's yellow, it's red, it's flashing. And there may be other attributes of objects that I haven't really thought through that,
Yeah. This is where the long tail of the world comes in, right?
Yeah.
Like you and I can sit here and we can talk and forever. Tesla's engineers can sit in a room and they can talk forever about this kind of stuff. And what happens is you're going to build a piece of code, you're going to put it out in the world, and it's going to find all kinds of things that you never didn't think about, right? So the right way to solve this problem is not for a bunch of smart people to just rack their brains trying to come up with every possible thing that could go wrong. You build something that's constrained in how it operates, you push it out into the world, and you look at where it fails. And then you take that information, you refine it, you push it out again, and you just keep doing that. And the thing is, the world is so perverse that you are never going to get to the end of the extraordinary situation.
Because an alien spaceship
is just going to become more and more rare.
Because an alien spaceship might land on the highway, right?
Yeah, or it's sinkholes.
Yeah.
I mean, who's driving down the road? Or have you seen that footage of those people who are like driving in coastal Japan when the tsunami came in? Like, oh, tsunami! I'm going to turn around and go uphill from here. Right?
Tidal wave.
There are things that you're just not going to see, and they're super common things that are also, things fall off of trucks. But what can fall off a truck? Anything can fall off a truck, right? I mean, something you've never seen. I drive down the road and see things on the back of flatbed trucks. I got no idea. Like, I'm an engineer. I think about machines all day long. I see metal contraptions on the back of trucks. I have no idea what those are. Or like, how am I going to train a neural network to recognize those individually? You have to treat them as a category, right? At some point, you're like, something, you have a category, which is stuff falling off of trucks, right? And it has to be able to recognize anything falling off a truck, right? And sort of understand that I probably want to avoid that thing that fell off the truck.
Human falling off truck might be more significant than squirrel falls off truck.
Or human falling off of motorcycle, or human falling off of bicycle.
Yeah.
So, old lady falling down in crosswalk. Yeah.
So I'm trying to get a grip. One of the things that I've been really trying to get a grip on, because I'm in Clubhouse, we have these conversations. There's some people who are like, and otherwhere there's people, it's never going to be good enough. And I'm like, I'm pretty sure it's getting close. Tesla has to be measuring how well it's performing internally. And it's not just like, I don't think interventions is really the dominant measure. Well, let me ask you the question this way.
It's not going to be numerically dominant.
Well,
they probably get 1,000 other trivial, notifications for every human intervention they get.
Right. So, well, I mean, one of my thoughts is that at some point it becomes better than human. And then the odds...
It's already better than human in lots of ways, right?
So when it's better...
It doesn't get drunk. It doesn't get tired. It doesn't adjust the radio. It's not yelling at its kids. It's, it's not fixated on the blonde and the, 2 lanes over. I mean, there's all kinds of failure modes it just doesn't have.
No, but what I meant was, where I was heading with that is, there's going to come a time when the human decides to intervene because he didn't see something the car saw. And the car, in other words, the car wouldn't go at an intersection because it saw something coming. And the human's like, why are we waiting? Hits the gas. And the car's like, nah, we're not going. But that's an intervention that would go back to the home office, dojo, whatever, to like evaluate, okay, what do we have to do here? At some point, the interventions become more likely incorrect. Like right now, an intervention is probably 75 to 90%. The car probably did something wrong. Somewhere down the road, an intervention is going to be like 10% chance the car did something wrong, 90% chance the human is wrong. And then at some point, it's like 99% chance the human's wrong. Because Elon has this saying that you want to get to the point where all input is error, right?
Yeah.
So
it kind of, I mean, I wouldn't be surprised if autopilot is already in a zone where most human interventions are unnecessary. So speaking of the human intervention thing, the worst Waymo accident ever was, it happened when, about this one
the human didn't intervene. The woman was...
No, this is one where the Waymo vehicle is coming to an intersection and it starts slowing down. And the driver looks at the situation and he doesn't see a good reason for it to slow down. So he overrides the car and goes. Well, Waymo saw a FedEx truck running the light, right? And the human driver didn't see it. The Waymo vehicle tried to stop. the human overrode it and got T-boned in the intersection.
Okay.
Right? So that was the worst.
I didn't know about that
they've
one.
ever had.
I didn't know. Yeah. The other one was when the most famous one is the woman is crossing the street and the Waymo driver's not paying attention. And the way she's crossing the street wearing dark clothing.
About the Uber accident in Arizona.
Oh, maybe that's an Uber accident. Yeah, you're right. It's Uber, not Waymo. But yeah, I mean, so anyway, I was trying to get to a point though, which is if we get to a point where interventions are no longer helpful in measuring how well it's doing and figuring out how to retrain the system, we have to rely on these other objective measures. We have to rely on flicker. We have to rely on, incorrect probability vectors. Something moved outside of what we anticipated with the probability vector. I like your points about, excessively hard braking, wobbly steering, inconsistent acceleration or braking. These all seem like good things to look at. When we hear Elon saying there's lots of improvements and version 9 is going to be really, really good, do you think that is they've been doing some internal measurements? They're measuring things like this and they're seeing better results?
Absolutely. And, without any serious doubt, the overwhelming majority of the feedback that they get right now into the system is not human interventions. Like they get a ton of feedback from other things that are not human interventions that help them refine the system. Those metrics they're relevant. They're going to continue to be relevant long after human beings, long after the steering wheel and the pedals are gone. There will still be all these metrics coming back to the car that they'll be using to refine the networks. But yeah, it's like, I mean, it's a nice talking point to say that interventions are really important because they are really important. And that's something that you can talk to somebody who drives the car or somebody who's contemplating driving one of these cars around. And they can say, oh yeah, I see this. If I intervene, it's a thing that goes back to Tesla or goes back to the AP team, and they can use that to refine the software. That's true. But for every human intervention, there's a whole space of other things that the vehicle is taking back. I mean, you were talking about flicker, but that's one example of one category, which is there's probably 1,000 categories, and there are probably dozens or hundreds of examples in each one of those. You probably can't get in your car and drive down the street without generating tons and tons of triggers that go back. Now, Tesla probably gets so much feedback from the fleet that they prioritize. Yeah. So like today, right now, we're working on this category of things. We're just going to look at those. They can accumulate this stuff. They can stick it in a database. Maybe someday they'll look at it. Maybe they won't. But they get an enormous amount of feedback from the fleet that doesn't necessarily require drivers to act in some way that's consistent and provides the feedback that you get. Driver feedback is important and it's very useful. And there are some kinds of things that you can get from driver feedback that you cannot easily get from the vehicle, right? But the feedback from the systems in the vehicle itself is just overwhelmingly larger than the human feedback.
Right.
And a lot of the human feedback, I mean, there's, I think, was it Karpathy talked about navigating intersections, right? So navigating intersections is an interesting, it's an interesting edge case in the world, right? Because most intersections are pretty consistent, but you've got some really, really weird intersections out there. And I mean, who hasn't come up to an intersection where you come up to the intersection and the city decided to paint a different number of lanes on one side of the intersection than the other side? You hit the intersection and you have to decide which of those slots your vehicle is going to go into. And sometimes you're off halfway. I mean, just looking straight ahead, you could go to this lane or that lane. And you have to kind of understand, what was there a right turn lane, a left turn lane? What are the lights in this thing? I mean, obviously you got to build the intersection so that it's obvious to a human that there's only one solution. You want to build the intersection so that a human being at a glance can tell what lane is the right lane for them to exit the intersection in. But sometimes those are things that you cannot write down, and just like it's hard to write in a short sentence, what's the difference between a dog and a cat? Knowing which lane you need to go into on the other. So a thing that you can do, and a thing that Tesla did do, right, is they started looking at what lane did the human driver take as they exited the thing. And so you train a neural network. Okay, here's the intersection. What lane do you think the human took when they exited the intersection, right? So humans drive lots of intersections, and you capture all these things. Like, here's the intersection. What do you think the human took? Now, occasionally you're going to get a human who changes the lanes in the middle of an intersection, and that's going to mess up your algorithm potentially. So you have to have some filters and stuff on that. But you can. This is a simple example of a large space of things where you can train the neural network to just predict what the human driver did, and that can give you an incredibly valuable way of labeling data for a neural network that you just couldn't get otherwise, right? That's a brilliant application, and there's 100 other ones like that too. Right. Is this stop sign relevant to me? I don't know. You probably, I drive nav on autopilot pretty much exclusively. I get in the car, I pick my destination, I set nav on autopilot, and, I fix it if something goes terribly wrong, but I just see where it goes. So my girlfriend and I, we do tons of long road trips. I've seen every kind of failure that you can imagine. And one that we see a lot these days, because the stop sign recognition has gotten pretty good, is like you're on some rural road and you're coming at some weird angle and there's a stop sign and it's bent, right? A truck has hit it. Or, it's an acute angle intersection and the car's coming up and you can see the stop sign. But the question is the stop sign for you or not? Like, that's actually pretty subtle. It can be hard to tell. And humans make this mistake all the time. They think the stop sign or the yield sign is relevant to them, but it's actually the adjacent road that it's for. So you can do a thing where you challenge a neural network, like, is that stop sign for me? Right? And then you look to see what humans do, because humans are mostly going to get it right. Like, if it's a traffic control in the real world that somebody hasn't bothered to fix yet, probably most humans are getting it right most of the time. So you get a good set of labeled data, and you can go on and on. I mean, there's all kinds of things like that. Like, should I drive over the curb here to enter the driveway, or should I, you can look to see, did humans drive over that curb in that spot or not, right?
Yeah. I did rear end somebody once. The human driver, 2 cars in front of me, mistook, we were on a freeway entrance ramp and there was another lane coming into our lane, and that lane had a yield sign, and he slammed on the brakes because he thought we had the yield sign. And I could not see this happening. The car in front of me suddenly swerves right, and I see a car stopping in front of me. So the guy in front of me clipped one corner, and I clipped the other corner of the guy. So human drivers get it wrong sometimes. So, and of course, I wasn't following with a safe enough distance to be able to stop when this happened in front of me. So I, as a human driver, was not perfect either.
Yeah, human pilot fail.
Human pilot, exactly. So we have all these triggers, all these things that maybe it didn't do just right. Actually, before I want to get to that, one of the thoughts I have in my head that I mentioned earlier was that there's some sort of, maybe it's predicting a probability of collision at any given moment. It's trying to minimize the probability of collision. It sees where all these objects are. It predicts where all these objects are going. It's trying to choose a path where I don't hit anything. Do you think it's doing some kind of measure of what's the probability what's the probability of I'd hit something on this drive, or what's the probability of collision per mile? Do you think it's doing any kind of calculation like that as a way of being able to evaluate how good are we doing?
I have not seen them attempt to produce a probability of collision. I think the utility of that is really low.
Well, you'd want it to be lower, though, right?
Yeah, it's.
I mean, your objective
that's
function.
a really hard thing to get a neural network to tell you, given the inputs that they have right now, I think.
So the reason I bring this up is
you would have to put a lot of effort into developing something that probably wouldn't be very useful if you were trying to do. Because, I mean, they have a lot of outputs which are, how should I turn the steering wheel to maintain a safe distance relative to this other object or this other vehicle? And like, that's a more directly and immediately useful metric that you get a lot of feedback on, right? Like how well you're doing. If I don't know if you remember the truck lust thing that we had on AP1, and when AP2 was new, like, people used to complain that you'd get close to a truck and the car would move towards the truck. So there was
Let me just interrupt you for a second. There's a thank you, Tactical Tesla, for your support. Tactical Tesla asks, automated DOT text message signs are quite important. Can a Tesla read those messages? Do you have any thoughts on that?
as far as I know, there's no support for that. I mean, they could have something, but it wouldn't be in any of the code that I've looked at.
Okay.
So I mainly look at the neural networks and the perception and that kind of stuff. I can ask, and Very Grain looks at this stuff, like he would probably know, but I haven't heard him say anything about it. So
okay,
I don't think it's in.
So sorry, I cut you off there. So the reason why I brought up this idea of the probability of collision is because I don't remember what it was, Elon Musk or Jim Keller. They were talking about this challenge of, like, I think it was like making a lane change in busy traffic, you know, merging onto a highway. There's certain situations where humans basically make the decision, okay, I have to do something where there's a non-zero probability of collision. Right.
That was Elon.
There's pedestrians walking or something, you know, you're trying to get through like a lot of pedestrians on the road and you sort of have to nudge forward.
Well, this is Elon at Autonomy Day. Somebody asked about like making lane changes in LA, and he was talking about how it was they will need a Mad Max Plus mode, and that maybe at some point they might have to allow people to accept a non-zero possibility of collision in order for the car to be assertive enough.
Right.
That like, I think that's probably not true. I could imagine that that there might be, you know, I mean, maybe they will eventually do that kind of thing. But when he's talking about a non-zero probability of collision, my take on that, I've listened to it a few times. I listen to Autonomy Day like every 6 months, I think.
Me too.
So I've been through it a few times.
I've been through it a few times, yeah.
Yeah. That what he was talking about is like taking the global view, right? It may be at some point in time that we want to give users the ability to dial the level of aggression up to a point where it's conceivable you could have a collision, right? That might, you know, that it's, I think a lot of people who drive regularly in Los Angeles traffic, and I do all the time and have for 30 years now, believe that that you have to be willing to accept a certain amount of risk if you're going to get where you're going in LA traffic. It's definitely a common perspective on Los Angeles traffic, that there is a non-trivial risk of having a collision every time you get in the car, even if you do everything right. Like, I think that's probably not true, but there are definitely people who feel that way. And there are people who are going to be upset. This is, interestingly, there are certain respects in which level 2 is actually harder than level 5.
Yeah.
Or level 4. And one of them is, in a level 2 system, you have to satisfy the driver's perception that the vehicle is driving the way they want to be perceived as driving, right? If they think the car is being rude or aggressive, or it's driving too close to the curbs, right, they will have a certain amount of dissatisfaction. But when if you ride in a taxi, I mean, there are some pretty lousy taxi drivers out there, right? But for the most part, when you're riding in a taxi, you let him deal with the driving,
right.
You know, and you don't really worry about it. And I think that, you know, FSD is not going to have to struggle as much with trying to satisfy the driver's ego, right? As long as it's not moving around too much and you're not getting car sick and you don't feel like you're in danger, you know, and you're not in a hurry to get to the airport or whatnot, you'll just let the car do the driving. But a lot of people today, especially people who pride themselves on their driving and are very interested in their driving, they tend to be very interventionist when it comes to the level 2 system, right? If it's not driving fast enough, they press on the gas. If they
I'm gonna diverge from the outline I want to ask you about, because you just triggered something I wanted to ask you about that I was talking about before. So I think that a lot of FSD drivers are more critical of the driving because they're sitting in the driver's seat. And if you were sitting in the passenger seat or the back seat of a car operating on FSD, you might actually be less judgmental of it. And I had this theory that you could do a Turing test for FSD where you're riding in the car, like if you were in the car, you would know whether someone was driving or not. But if you were riding in the car behind and you were observing the car and you had to decide, is a human driving it or is FSD driving it? Is one of the goals to get to the point where the human behind can't tell? Or would FSD be so good you would know right away, wow, it's staying perfectly in its lane all the time, it must be the car driving? But is there some value in trying to evaluate how it's driving, not from the driver's seat, but from the passenger seat or from a car behind?
Maybe. I have an interesting anecdote that a friend told me. After a recent autopilot used to not be able to drive up PCH, the one freeway up the
Yeah.
coast. Like it was like I've been up that a bunch of times on a bunch of different autopilot versions, and it was really horrifyingly bad for a really long time. And then it got to where it could kind of do it. And then they, in 2018, they pushed out an update, and suddenly it could do it. Right? So a friend of mine was driving up PCH in a Model 3.
So, sorry, for those who don't know, PCH is Pacific Coast Highway. I used to live right off it in Half Moon Bay, California. So, it goes all the way.
It's a coastal road. There are cliffs in a lot of places. It's super windy.
People die. People die on PCH. Or I should say people die falling off PCH.
The traffic is highly variable. A lot of people drive too fast on it. There are lots of places where the road markings aren't great or the road barriers aren't great or whatnot. But it's a curvy road. It's got decent speeds, 30, 50, 60 miles an hour for long stretches of it. And some places it's really windy. Anyway, so an acquaintance of mine, he had just got this new push, and he and his wife happened to be driving up PCH, and he got in the car. And they started driving up PCH, and he flipped on autopilot, and it was driving, and they were, he just let the car drive up PCH for like 90 minutes or something. And then at some point they pulled over to one of those scenic there's all these viewpoints where you can stop and take pictures of rocks or seagulls or whatever. So he did that. He got back in the car with his wife, and he got back on the highway, and he turned on autopilot, right? And his wife heard the chimes when it activated. She said, "What, are you out of your mind? You can't turn that on this road." And then he was like, "It's been driving for 2 hours." And she had no idea.
Right.
So I love that anecdote because I think she probably, my sense from hearing him talk about his wife and autopilot over the years is that she would have been really nervous on that drive the whole time they were doing it if she'd known autopilot was driving the car.
Right.
But somehow she didn't hear the activation chime when he turned it on, and it was fine. And she couldn't tell it wasn't him driving.
Right. Sorry, just 1 second. There was a good comment. I want to ask this guy. He says there's been an observational Turing test with FSD Beta. I think it's on YouTube AI drivers. So I just asked because I won't see the chat later. So Frederick, if you could put that in the comments, I would like to see that. So okay, we kind of covered that point that I think that but do you agree that people are more judgmental of it when they're in the driver's seat than they might be if they were in a passenger seat or in another car?
I believe there are people where that's true. Yes.
Okay.
I believe that is true. People's reaction and experience with autopilot varies a lot, and for autopilot changes over time. People's comfort level changes with it, and your comfort level can be highly varied. People who drive all the time in the city with it can feel weird using it on country roads. People who drive on rural roads, they can be terrified in the city. It's a complicated beast. It has a lot of it has a lot of behaviors that might seem kind of strange, and then you get used to them and they just seem right after that. And so, I know maybe a few dozen people who use autopilot heavily, and they run the gamut from people who only use it under absolutely ideal circumstances. I know a lot of people where, like, if they ever have a intervention, like, they never use autopilot on that road again, right? Because interventions upset them so much.
Right.
And then I know plenty of people who are like me, or like I'll drive some crazy mountain road and I'll turn on autopilot and I'll be, it's like, how can it do this hairpin curve? Like, where will I have to intervene?
Right.
And, I'll do that all day long, and it doesn't bother me at all.
Right. Well, I'm not at your level, but I wrote code from middle school through grad school. And, one of the goals is, we got to see if we can break it. Right. Let's see if I can make it not work. Right. That's kind of what you do with code.
I've noticed recently, I've been trying to understand how the camera integration works for the BEV networks. Right. So I noticed they started pushing. What is a BEV network? Sorry, there's the way that the system integrates perception across cameras has gone through this quite large change recently, like over the last 12 or 18 months, but it's really accelerated recently. And I noticed when I saw the first FSD code that they were making heavy use of this. So once upon a time, a couple of years ago, each one of the networks, we were talking about how there's these perception systems, and then you have this code, this human written code that sits on top of it that takes the perceptions and makes decisions. Well, once upon a time, that human written code was looking at separate inputs from each camera, right? So the human written code would have to say, well, what does this front camera see? What does this front camera see? What does this front camera see? And then make decisions about driving. So ideally what you want is you want a neural network to integrate all the cameras to create a comprehensive sort of understanding of the scene. And there's many reasons why that is superior. But there's also many reasons why it's actually hard to do. And so I think Tesla tried for a while to figure out how to get this working. Then about 2 years ago, they came up with an approach that they liked, and they've been gradually refining that approach. So the approach that they use is we call it bird's eye view network.
Bird's eye view. Bev network is bird's eye view. Got it.
Yeah, BEV is a bird's eye view network. So
let me just pause you for a second, because Alter Ferguson Financial says, and thank you, Bradford. The world needs more of James Douma. Good to see you, Jimma. What do you think about all the major rewrites Tesla has been through? And if not discussed, what do you think the current wait is for getting V9 to limited beta? So let's interrupt to, what do you think about all the major rewrites Tesla has been through? That's kind of a broad question.
I think it's necessary to make that. So Tesla's MO for doing this, which I'm a big proponent of making this happen as quickly as possible and getting it out into the world, and being willing to take a certain amount of risk. 1 million people a year die in vehicle-related accidents in the world every year. 50 times that many people go to the hospital. Trillions of dollars of property damage are done by this. I mean, this is a very important problem to solve. So, taking an extra 5 or 10 years to solve this problem, to me, does not seem like a good idea. We should be willing to push the envelope a little bit prudently. We should be willing to try something, and if it's not working well, back off, right? But we should be willing to try things. We should not be in a situation where we are not going to try something in the real world until we are absolutely certain that there will be zero negative consequences to it at all,
right,
because that's just going to slow down the pace at which we can do this. So if you're going to be a little bit aggressive, you want to constantly be making iterative changes, and you want to be willing to regress those things and make adjustments based on what you see in the real world. So this is what I see Tesla doing. So major rewrites, if you're doing a lot of experiments to try to understand how to do a particular thing, and you do a bunch of experiments and you discover that no incremental changes that you're making actually are going to solve this thing that you need to solve to get to the next level, occasionally you have to stop and you have to say, okay, we're going to have to change this fundamental stuff, and it's going to take a while, because we're going to have to write it. We got to get it working. We have to change the training software. We have to get all this extra data for our training corpus. We might have to change the way the training software works in the background, not just the labeling software. And then we got to push it out to employees. Then we push it out to the alpha testers. Then we push it out to the beta testers. You get feedback from all those things. You modify, you update it, and that kind of stuff. And eventually you get to a point where you can push it out to a small number, maybe 1,000 or 5,000 or 10,000 people, who haven't signed up for this.
Right.
Right. Maybe you have to push it out in shadow mode first. So that process, if it's a tough problem you're trying to address, and it's important enough that you're willing to take a time out to do a rewrite in order to do this stuff, it's a thing that has to happen. It typically leads to a pause in the incremental updates we get as they focus more and more resources on getting this thing out. Then you see the thing where the code comes out, every day people get in their cars and you drive it, and there are these things it can do that are amazing that it couldn't do before, and you're so happy about that. But it's also got 50 bugs that are driving you crazy, right? And so you've got these 50 new bugs. And for a week or 2 weeks, they get a whole bunch of updates. And then a month later, the bugs are mainly solved, and it's all just great. You've gotten up another level. So personally, I'm super excited when they do a rewrite, when there's a big pause, because my experience with the pauses has been that they have always been worth it. There's always been a very significant step up in functionality a month or two after they start pushing the updates again. So like, I'm super excited about V9. If they took a pause on V9, it's because they came up with something that was important enough and valuable enough that it was worth taking time out in order to go attack that. And my experience is that every time they've done that in the past, it's been a significant improvement in performance. And so I expect V9 to be really good. When I see them take a pause in pushing the stuff out, like, my experience is that it's always been worth it in the past, and I expect that this time too.
So the second part of Bradford's question was, if not discussed, what do you think the current wait is for getting V9 to limited beta? I would ask it a different way. Is there a chance that V9 is already on some beta cars operating in shadow mode, like on the second chip, or is it unlikely that they've pushed it in that way yet?
So V9 is already operating on employing cars. Like, there are people who are driving.
No, but I mean, like, you've got people who are FSD beta drivers. Is there a chance that they've put V9 on beta cars, and, you know, like, the one chip is operating with V8.3 and another chip is actually in shadow mode operating on V9? Or is that unlikely?
Yeah, that's not the way shadow mode generally works. They don't push to complete versions and then drive one. The shadow mode is generally for testing features. So they'll add a feature, and that feature will run in shadow mode, and they'll evaluate that feature. Typically, now, so here's the question is, whatever feature it was that they changed in V9, is it small enough that they could stick that in shadow mode on FSD beta cars? My guess is the FSD beta crew isn't big enough to probably make it worth trying to do that, because they have 300, 500 internal testers at Tesla, right? And you don't have to, you can give them the thing, and you can give them complicated rules, and you take all the liability, and you don't have to worry about it, it leaking out in public, because they're all under NDA and so on. So my guess is they'll probably do that refinement with completely internal testing. And when they push it out to the beta, to the FSD beta crew, they'll probably tell them. I mean, the public FSD beta crew is only like 20 people, right?
Okay. So, and do you think that version 9 will be coming out to FSD beta testers soon? Like, do you have a prediction? Is it a week away? Is it 5 weeks away? Or we can't know?
I don't think it's months away. The tail end of these kinds of things is that, you have this metric that you've settled on internally as a team. Like, we're going to push this when this number gets to X, right? We have to see no regression on all our regression tests. And this thing that we're trying to get to, it has to get to at least 9, right? And so, you push it out to a bunch of people, and they push it, and it comes back, and you're saying, it's at 8.2. And you look at what the deal is, like, do we just need more data? Do we need to tweak something? You do some tweaks, you push it out. Eventually you cross 9. The closer you get to that number, the harder it is to actually predict in a weird kind of way. Like, 3 months ahead of time, you can look at it and say, well, we think it's about 3 months, and you might be pretty close. But when you're actually a week from it, you don't know if something's going to happen that's going to cost you 4 weeks or not, right? So, like, the percentage uncertainty as you get closer to the day actually gets really big. So, like, given the level of my experience, I mean, everybody else here has probably listened to Elon's predictions and Andre's predictions and watched this whole arc. So I'm sure you know what I know. Technically, the only insight I can give you is that it's actually weirdly hard to make the predictions the closer that they come to fruition. So I'm pretty hesitant to put my name on a prediction on that.
Okay.
Right now.
So I just want to skip ahead to something. The chip in the car is known, or the chips in the car are known as inference chips. And I believe that comes from a concept called Bayesian inference. Are you familiar with Bayesian inference? No? Or that's not what it is?
It does not come from Bayesian inference.
Okay. What does it mean that it's an inference chip?
So with neural networks, a neural network kind of has 2 modes that you operate it in. One is where you're training it, and one is where you're taking a fully trained network and you're just using it to evaluate something. In the field, using a fully trained neural network to evaluate an input and provide an output, that's called inference. So inference chips are chips that are designed specifically to perform well on the task of inference without regard to training.
Right.
So
well, the data comes in.
Also,
there's weights assigned to the neural network, and the data goes through the neural network, gets processed, gets assigned weights, and it goes through this whole process, and out comes which way are we going, right? I mean, and then the training is let's adjust the weights. Am I in the ballpark right there?
Yeah, training is finding the set of weights that will give you the target performance given the network architecture that you're working with. So all of Tesla's training happens in a data center, right?
Yeah.
That does not happen on the car. In fact, the hardware in the cars isn't capable of doing training. It would be really, really hard to write software.
Let me just, this is a question that's come up before, and there's actually a video that shows this. My impression is that the car does not learn between updates. So there's this video I saw where the car is like driving down the road, and it comes to this particularly challenging right turn. It's just like, where are you supposed to go to make this right turn is not clear. And it goes through it twice and it gets it wrong, and then the third time it gets it right. And my theory about it is the inputs were slightly different. Like what the pixels were that came into the chip were different on each occasion. It's not that the car got better at handling the intersection. It's that it just saw different inputs. And then if it got retrained a week later, it might handle the intersection better. But if it performs differently at that intersection, it's because you didn't notice changes in the pixels, because there could be subtle changes in the pixels that you would notice.
Right.
Okay.
Yeah, the flicker was right on the time that it. Now there's when you're evaluating a new piece of software, like the FSD beta testers, they're frequently in this mode where they've got an update and they're out there trying stuff, right? They're trying to understand what the car can do. And they're paying close attention to all this sort of easily human perceptible behaviors that the car has. And when you drive a route that you've driven, most of the beta testers, this is true for me on the way that I use the cars, like I have all these benchmark routes that I drive. I get a new version. I have these 4 or 5, failure modes that I know that the car has, and I take it out and I drive it on the failed stuff to try to understand how its behavior has changed on those things. So a lot of the beta testers have those kinds of things. So they have routes that they drive pretty regularly, and they'll notice where it performs well, where it doesn't perform well. There's a certain amount of statistical variation that you're going to get in any sort of subtle, like doing. Like what constitutes a good right turn is kind of a subtle thing. Did it do it fast enough? Was it too close to the car ahead of me? Like, was it too close to the curb? Did it behave in a way where some other driver might think I was doing something weird? There are all of these highly subjective, difficult to describe characteristics that go into that. So a human being goes into, that you do a long drive, it's got 20 turns and 50 stop signs and a bunch of cars around you, and you notice a half dozen things that it doesn't do very well. But those are a half dozen things that you're noticing out of maybe 1,000 things that's happening on even a 5-minute drive, right?
Yeah.
So you notice those as a problem. Then you drive it a couple more times, right? And now you're keyed to look for particular things. Like there were the 5 things that bugged you on the previous drive. So it might do some other things poorly that it did well on the first drive, but you don't notice those as much because you're keyed to look for these particular things that you were failing on, and they've become a benchmark for you. So you drive it a couple of times, and it works some number of times, and it fails some number of times. Well, humans will categorically look at a sequence of success failure modes. If you do it 5 times and you see failure, 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 success, success. So there are 32 possible combinations in there, right? But that combination has meaning to a human, right? If you get 3, so maybe of the 32 possible combinations of 5 sequential events that you can get, there's a couple of them that a human being will ascribe meaning to. And frequently the meaning they will ascribe is it's getting better or it's getting worse, because you often see people say, oh God, it's regressed or whatever on this random test that I did. The reality is these are statistical samples from a space of possibilities. And there are some that people notice. And it's very easy to convince yourself that what you're seeing is statistically significant when it is not.
Right.
If they go out and they keep driving that thing, if you really want to convince yourself that it's learning, do this. See at least 4 failures, and then see at least 4 successes with no subsequent. That's statistically unlikely.
Right.
But 3 successes and 2 or 3 failures and 2 successes, that's statistically in the noise.
Right. Well, so
And that's what most people who are speculating that it learns in the car, they're doing that on the basis of like 5 evaluations.
right. Well, there's a subjectivity
20.
to it, though. There's a subjective nature to it that you feel like it's driving. Well, there's two different things. One is you have a limited amount of experience. You do something 3 or 4 times and you feel like it did it better the last time. That's just not enough data. And there's the other thing, which is you drive the same route. It feels like it didn't do it as well, but for all you know, there were different inputs you didn't notice, right?
Yeah, you're only capable of paying so much attention to so many things that happen in a 5-minute drive, right? And the first time you might be a blank slate, or you might have some perceptions, but you're going to be keyed to look at particular things that you kind of priority perceive as important to what is going on, and you won't notice the other 995 things that happened on that drive.
So Halter Ferguson Financial again. This is sort of off, a little bit off, but does it, I didn't hear this. Does it concern you at all that Elon seemed uncertain on the Q1 call that the eventual level 5 solution may not fit into the car? So before you answer that question, I just want to ask you, do you think the levels matter? Do you think that this ASE level system matters?
Like, everybody in the self-driving car business thinks the levels are stupid. Okay. Some people still use them to talk about stuff because they are a useful construct for talking about the problem in certain respects, but people on the technical end of things generally think that from a technical standpoint, it's a lousy categorization system, right? And they don't really like to use it. And I think, you know, I have not heard Elon lead with saying level 2 or level 5 or something himself. Occasionally, he'll be asked specifically a question. Oh, will this level 2 thing or will this level thing? And occasionally, he will respond using the terminology that the question was phrased in, but I've never seen him initiate that. And frankly, most of the people I know who are in the space, they don't like using the levels.
Right. But so,
you know, it's kind of George Hotz has this take on it, which I think is kind of interesting, where he points out that it's really, the levels are really a liability question. They don't really say anything about the technical capability, right? Like if you have a system that could technically drive level 5, but you require a driver to drive it, well, now it's a level 2 system. So it's not saying anything about the vehicle's technical capabilities. What it's saying is, you know, is the company that pushed this out gutsy enough to take responsibility for it, right? Because that's when it's level 5, when the liability shifts to the organization and not the driver.
Okay, so this question, let's take it away from the eventual level 5 solution. The ultimate goal of Tesla is to have software that can drive the car without human supervision. You can take the steering wheel off. I didn't hear Elon say this, but did you hear it? And does it concern you that Elon seemed uncertain that this ultimate solution would not fit into the car? I think he's talking about the chips and the existing hardware. I did not hear that, so I don't know. Did you hear that in the Q1 call?
Yeah, I didn't get that. I mean, Elon seemed really off on the.
Yeah, he did.
On the recent call. He seemed really, I mean, what do I know? But he seemed really tired and kind of out of it. Maybe he was distracted or whatnot.
Well, you heard the baby in the background, right?
He definitely was not his upbeat, you know, funky, you know, cheerful self.
Yeah. So, all right. So let me move on to this other question. There's this thing called Dojo. So you mentioned before that there's this data center where they do training. And Dojo is apparently going to be an update or an improved system for doing training. So the current training is like a GPU cluster, as far as we know.
Yeah, they're probably using a GPU cluster. Yeah.
And the next step is at some point they're going to deploy Dojo, and Dojo is, I don't know, I think I saw 16-bit floating point processors, and there's some other stuff going on there. What's your impression of what the difference is likely to be between what they currently do and what Dojo will be doing at a hardware level?
So there's no silicon for training neural networks in the world today, which was developed from scratch with the intention of training neural networks, right? So every system that's used in the world today, to a greater or lesser extent, is something that was originally designed for some other purpose, which has been adapted to train neural networks. There really hasn't been a clean sheet of paper design for a piece of silicon. If you really want to train neural networks at scale, big neural networks at scale, the cost of computation becomes really important over the long run. Like maybe not for your first 2 or 3, but you know, Andre said 18 months ago that they were spending 70,000 GPU hours to do one full training pass on the networks that were going in the car. Now, those networks were a lot smaller than the networks are today. 70,000 GPU hours is 3 days on 1,000 GPU cluster, right?
Okay.
Now, they do a test forward development methodology at Tesla right now. At least this is how Andre has talked about it. So one of the things they do is they train the neural network. They train these things over and over and over and over again to evaluate how changes that they're thinking about might have an impact. So they would like to train this thing 100 times a day. They would like to be able to make very small changes to it and retrain the whole network to understand how things interact. I mean, they're training limited. They have a number of things that limit them, but the amount of computation they have for training the networks it's a kind of piece of low-hanging fruit. Like if they had 100 times as much computation to use in training, they could move faster. They could refine this network much more quickly. Right?
Well, that's what I was going to.
So in that sense, they're computation limited.
I was going to ask.
So I think
I was going to ask you about that. What I see with Dojo is there's two things. There's when you do your training, an individual training session, Dojo might lead to greater improvement than with the GPU cluster. And the other theory is you'd be able to do more frequent training. So are those...
Being able to do more frequent training is very useful, and that will be a benefit of Dojo. But there are also training approaches that they are not doing right now because the computational intensity of some of these approaches is high enough that they can't fit it into their current development regime. Like if you try a training approach that takes 100 days on 1,000 GPU cluster, like they can't do that right now, right? There are no questions that they're asking about the network that they're willing to wait 100 days to get an answer to. Right. So this 4D training from video thing it's going to be horrendously computationally intensive to scale that up. Like if you really want to do all your training that way, you really need a lot of computation. So, you can go to Amazon, you can build your own data cluster. There's different ways you can get this, right? But at the end of the day, there's this piece of low-hanging fruit that nobody on this neural network training thing that isn't really being pursued right now, which is you could design a computer from scratch that was just designed to train neural networks. Like you're not going to use it for anything else. You don't care about anything else. You're going to clean sheet. You're going to design it. That's what Dojo is. It's Tesla saying, we have this MO. We just want to train neural networks. And, and this is something that we're going to use enough of this that it's going to save us billions of dollars a year at some point. So we're going to develop it now so that 5 years from now, instead of giving the money to AWS or giving the money to NVIDIA or somebody, we're going to, the same thing they did in their car. We're going to build a chip that's 10 times as performant, that takes 10 times less power, and that costs 10 times less money. Except it's not just a chip, right? I mean, we talk about the silicon aspect, and for Dojo, silicon, it's an important component of the thing. But to build a cluster architecture or an HPC, a high performance computer, right? A data center that's targeted. There are a lot of other really important things, like there's the thermal performance of the thing, there's the networking performance of the thing, there's packaging, there's storage, there are a bunch of components of building that machine that you have to work through, in addition to just designing the silicon and getting it working. And I think Dojo is basically Tesla saying, we need computation to be 10x cheaper. We need it to be 100x cheaper, and that's not on anybody's roadmap. That's not on NVIDIA's roadmap right now. That's not on Intel's roadmap. That's not on the roadmap. It could be that somebody that Keller's got a new company that he just signed on to being an employee on that's working on this problem. Somebody else could come up with something, and that would be great. Tesla could just adopt that.
Somebody in China could be doing it.
Yeah, sure, it could be.
Yeah,
it's possible, but they don't want to wait for somebody else to solve the problem. It's too important a problem for them to them for this effort that they're engaged in. So Dojo's their effort to make that box.
So the gain here is to be able to take on more challenging computational approaches to training, and also to be able to train more frequently, or to try different approaches to training maybe and see which one worked better.
Yeah. Right.
And then so one of the thoughts I had was people who have FSD are used to seeing an update, let's say once a week or once every 2 weeks. And all of a sudden they might start seeing updates every 2 or 3 days. Is that possible, or is that not likely to happen?
No, I don't think it'll manifest that way. So internally, you might have a team. So Andre's had a couple of good videos where he talks about, how they organize the autopilot team in terms of doing multitask training. Multitask training is you have a single neural network, but you want it to do 100 different things. The reason you're doing a single neural network to do 100 different things is because these different things you're doing, they have a lot in common. And so it's computationally efficient to basically try to put that all into a single network. But there's trade-offs between these different tasks. And then the trade-offs in the task will be, how much accuracy do I have for a particular task? So I have a single neural network. It's giving me 100 different outputs. And there's a trade-off in the accuracy between output 3 and output 5, right? And so I have a training corpus, and I have a certain loss function, which basically determines for the overall network, when I train it, what constitutes success in training. Like, what do I want it to go to? The nature of that loss function, the way you build it, it will create, part of it is a trade-off between, like, how important is output 3 versus output 5. Then there's what goes into the training corpus, right? Because you can put more examples that are designed to make output 3 better in the training corpus, or you could put more examples that are designed to put. Sometimes there are these fundamental trade-offs that you have, and a lot of problems with trying to train these networks are complicated enough that the only way to know the effect of a change is to do the change, right? So you've got a guy whose job is to, like, get some particular aspect of the network to improve some particular aspect of the network, and he's playing around with stuff, but he doesn't know, as he makes these changes, how they affect other things that the network also has to do. So it would be great if you could just train the network and ask it, right? But it takes 3 days on this giant cluster, and they might have 100 of these problems that they're working on simultaneously, right? So they've got 20 guys, 100 problems, and it takes 3 days to retrain the network from scratch. So what do you do? So effectively, what they have to do is get very clever about training parts of the network and doing kinds of trade-offs, and then hoping when you put it all back together, you get the result that you want. Sometimes you don't, and you have to go back and do it again. If you could just train the network, right, you could get to that answer more quickly with more assurance of what's going on. And that's just really computationally intensive. And maybe they don't have the compute resources, or they don't have the budget to do it right now. But if their computer was 10 times faster and 10 times cheaper, then they could do it, right? So their development gets faster, but that doesn't necessarily mean that they push more versions out. It just means that they get the answers to the questions the development team has more quickly with less manpower.
Okay, so we have a question from Not Financial Advice. Thank you for your support. What year will FSD be good enough for a wide-scale robotaxi launch? Best guess. So I'm going to offer my opinion that by the end of this year, FSD will be operating somewhere in the world, possibly Florida. Not robotaxi, but FSD will be operating somewhere in the world better than human. And, probably still going to be required to have a human operating, there, but it's going to be driving better than human. And then robotaxis by the end of next year. What are your thoughts on when we start to see some kind of robotaxi launch?
So that's approximately my guess, is similar to, but I think Dave asked me this question, maybe Rob asked me this question the other day, and I said, if you'd asked me a year ago, I would have said the same thing. So that's worth keeping in mind, right? Is that it was my feeling a year ago that we were a year away from seeing it functioning technically good enough in a significant number of circumstances. So the first version isn't going to work perfectly for robotaxi every place, right? There's definitely a hierarchy of situations, and we're going to see it come out. It's going to have some capability, and that capability is gradually going to improve. At some point, the capability is going to be good enough that it can reliably drive end to end in a significant number of useful routes, right? And maybe that would be the point at which we would say, okay, FSD is working, right? It's not level 5. It doesn't work everywhere, but it works in plenty of interesting, economically useful circumstances, right?
Right.
So how long after that do we get to flip the switch, and actually take a nap or read a book or, play a video game while the car is driving? I think that's probably like a year. I think we get there, and it's a year before Tesla says, okay, you don't need to pay attention.
Well,
So that's why
do you
I
think
say,
Dojo
I think
accelerates
it's a
the
couple
learning?
years. What's
Do you
that?
think Dojo accelerates the learning?
I think Dojo accelerates the rate at which the actual performance of FSD improves.
Yeah. Okay. I probably didn't say it that well. That's what I meant. Okay. So I want to move on to a different topic here, which relates to Dojo. My theory is at some point, FSD will be essentially solved. As in, it will be working significantly better than human, and that's like in all circumstances. And there might be better things for Dojo to do than train FSD. Or you might build another Dojo to do other things. Once you've figured out, hey, this Dojo thing works pretty good, let's see what else we can do with it. Either we keep using it for FSD or we create another one to do something else. So one of the thoughts I had was, I was going to sort of talk generally about what else could you use a neural network training computer for. I'm guessing broadly a lot of things, but one of the thoughts that I'm fascinated by Neuralink. I don't know if you know this, a lot of my followers know this. My mother has Alzheimer's, my grandmother had Alzheimer's. I consider myself at high risk for getting Alzheimer's in, say, 15, 20 years, if not sooner, but probably 20, 25 years. So I'm very excited about the prospect of Neuralink being able to maybe either help us understand Alzheimer's or maybe cure it. And one of the things that, as I see what's happening with Neuralink, is the chip goes in the brain, and the chip is reading signals. There's electrodes going into the, let's say, the motor cortex right now, or various parts of the brain, and they're picking up signals from different neurons. Could Dojo be used to interpret the signals coming from the neurons? Is that a use for an AI neural? I mean, we're trying to understand a neural network. Could a neural network training computer, neural network inference chip be a part of the process of understanding what's coming out of the brain?
Yes. I'm not sure if so. One of the neural networks actually work really well with the whole idea of Neuralink, right? When I say neural networks now, I'm talking about deep learning neural networks like this computational metaphor that we're currently operating in. The concept is fundamentally sort of mimicking what we understand about what the brain does, right? I mean, brains have nerve cells. They have a large number of them. They're interconnected. The information processing capability is largely captured in the way in which these things are interconnected. The weights in a neural network are mimics of the processing that neural tissue does, right? I mean, it's different in a lot of important ways, but it's very similar in some really fundamental ways also. If the brain wasn't designed to have chips inserted into it, right? That wasn't one of its evolutionary priors. So, however, the brain is extremely plastic. Like its ability to learn things, it's shocking how plastic especially the human neocortex is. It's amazingly plastic. Its ability to reconfigure itself to deal with new situations is stunning. And one of the things that these brain implant experiments have shown us is that if you can achieve biocompatibility with the tissue, the brain is happy to adapt itself to your interface, right? But the interface, it can only, the nature of its adaptation is always going to be this broad-based thing. Like I have a large number of neurons, they're expressing this complicated, subtle abstraction, and I need to be able to interface to that, right? I need to be able to stimulate that abstraction. I need to be able to extract that abstraction. And neural networks are really a great way to go at trying to understand that abstraction. Essentially, I imagine this thing where you've got this interface between these two different kinds of neural tissue that are going on. You've got this biological neural tissue in the brain, which is trying to adapt to this interface, right? And you have this silicon version of a similar process happening on the other side. They're trying to come up with a language that they can speak to each other to achieve some sort of goal function that they're on. And I think, using neural network type computational methods on the interface side is a really promising way to try to quickly realize the promise of a neural interface. Right? I'm very excited about that possibility. Incidentally, I think if I was worried about Alzheimer's and my window is 25 years, I don't know if Neuralink is necessarily where I would be placing my bets right now. There are a lot of promising Alzheimer's treatments in the works that that address that problem in other ways. The way to use Neuralink to go after, there are a lot of things that Neuralink is going to be able to address pretty directly, pretty quickly, once it gets to a certain level of safety and efficacy for basic interfaces, right? And Alzheimer's is it's on that list some point, but it's not one of the early ones.
I agree with
right?
that. I agree.
Yeah.
Paralysis,
Alzheimer's,
paralysis
trying to
and
deal
blindness.
with it with
I think paralysis and blindness are high on the list.
Yeah, I mean, there's anything where you've got a brain lesion, right?
Yeah.
Or you have some highly localized chunk of functionality that you're trying to submit for. The problem with Alzheimer's is it's highly distributed, failure in brain tissue,
right?
And I think Neuralink functioning as an augment to help support functions that are degrading in Alzheimer's is, that's something that you can get to relatively quickly, but it's going to be a crutch.
Well, let me ask it a different way then. Do you think, well, first of all, I want to thank you because you answered my question. I asked you a question that was very poorly worded and you came up with an answer to the question I should have been asking, or maybe I meant to ask. So I really appreciate that. But I guess my thought is not necessarily that Neuralink will cure Alzheimer's only, but that it might help us understand it better. That we might be able, because I having gone through this with my mom and having looked at what the clinical trials are, we have a doctor in reasonably close proximity. We were referred by my mom's doctor to a doctor who's doing clinical trials on drugs, and I read the clinical trial papers on all 4 clinical trial drugs that we considered. And this is only like 2 or 3 years ago. They are nowhere close to solving out, at least not what I saw. In my limited experience, they are nowhere close to figuring out. They don't even know what's happening yet. Is it plaque? Is it the tau protein? There's all these different theories and no one knows. And one of my thoughts is that if you had Neuralink chips in the brain and then you gave a drug, you gave somebody Aricept, or you gave somebody galantamine, or you gave somebody Namenda, and you were able to see how did that affect brain function. That might give you some insight into what's going on. It may be that we'll be able to do much better clinical trials when we can measure what's going on in the brain while we're doing things. Like the solution...
It'll give you a kind of objective evaluation of how an intervention affects brain function that cannot be acquired.
Oh, you just
today. Now, fMRI is, there are some really great techniques for seeing what's happening inside the brain and evaluating stuff. And there are a lot of things. If you had to choose between Neuralink and fMRI probably wins. Right? It can see deeper. It can see, more kind of global phenomena. Right? You can see chemical gradients. You can see all this kind of stuff. But there are basic functional metrics that you could evaluate with Neuralink, which are not going to be accessible to fMRI because the resolution just isn't high enough. Right?
Yeah. Well, no, it's funny when you mention objective because my experience with my mother is I don't really have objective measures of how my mother's changed. Right. And I will say this. My mother is basically a zombie at this point. I mean, she can eat. She can participate in activities. She might know who I am on a given day. She might not. She's not capable of higher reasoning of any sense at all. Right. She doesn't know where she is. I'm not sure she always knows who she is. So she's pretty far gone. But I don't have like a chart where I can chart like details of how she's doing and be able to measure things objectively. And I think I hadn't thought of it this way, but Neuralink could be a way. I kind of said it, but I think you explained it better. As again, you explained it better than I did. You might be able to use Neuralink to better measure how the brain is functioning, and maybe fMRI is another way of measuring how the brain is functioning.
Yeah, some things you can measure. You'll be able to measure better with Neuralink.
Yeah.
And one of the things about Neuralink is you can do stimulation directly, right?
Right.
fMRI you can't use to stimulate the brain. You can't use to mimic a drug or any of that sort of stuff. And one of the problems with evaluating a system that's as complicated as a human brain is, the plasticity confounds your ability to measure stuff because it can adapt so quickly to its circumstances that frequently it's difficult to understand what component of the observation you have is due to the brain attempting to adapt around the problem that it has, and how much of it is fundamentally the problem itself.
Right.
But anyway, I'm very sorry to hear about your difficulties with your mom. That must be a very difficult thing to go through.
It's actually, of course it's difficult, but because we went through it with my grandmother, and because my mother basically, and I was an adult when we went through it with my grandmother, and my mother basically prepped me. Like, she took me to seminars. She anticipated this might happen to her. So she helped me prep for it. And my goal has been keep my mother comfortable and happy. And my mother has this great long-term care policy that's like, it's insane how much we make money off my mother having Alzheimer's. It's crazy. My mother's basically netting like $10,000 a month because she chose this great long-term care policy 23 years ago. So financially, it's fine. I got her in a place that's 3 minutes from my house, and 3 minutes from my house, and I can check on her except for COVID, I've been able to check on her frequently, see her a lot. But she's comfortable and happy. That's all I can hope for. But sorry. So I wanted to
keep your inflammation levels really low.
Yeah.
Right. There are great biomarkers for inflammation. It's known to be a major input, and there are all kinds of lifestyle changes that powerfully influence the level of inflammation, passive inflammation, and that you.
Yeah, my mother followed a vegan diet for over 20 years, and I wouldn't be surprised if that put it off 2 years. Like, she might have been affected 2 years later than her mother. So I think there's some benefit, but there's a lot of people have a lot of ideas. Oh, do puzzles, do this, be active. Most of the ideas people have, they don't necessarily matter a whole lot. And in my opinion, the medicines might work for some people, but they did not work for my mom. So I want to turn to a question I meant to ask you during we were talking about FSD. Maybe I'm going to ask you this question first. What is shadow mode?
Yeah, so shadow mode is it's a broad term that actually captures a lot of different sort of specific techniques. But the general idea with shadow mode is that you're putting a bit of functionality into the vehicle, which is not going to be used to drive the vehicle. You're going to use the vehicle as a test mule, and you're going to run this function silent in the sense that the user will not observe any behavioral change in the vehicle because this thing is in there. But with this function in the vehicle, you can have you can have a test function in the vehicle that's evaluating the performance of this thing that's running while the vehicle is out there driving around in the real world. So shadow mode is generally putting functions in the car that do not benefit the car's driving immediately, but they generate useful data for Tesla to help it improve. So that could be a way of pre-formatting data that goes into a neural network, or using a particular output from the neural network to achieve a problem as opposed to what the car is currently driving. Or it could be a relatively sophisticated function that you're thinking about pushing out to the fleet, but you want to see it run for a little while to understand, what's the failure rate before I turn this on. So the cut-ins ran in shadow mode for a while. Carpathy talked about the cut-in detector, right?
Yes.
Now that was a great example. Like, I love the cut-in detector example because I went through this with my sister. My sister got her Model 3 and was going through, getting used to using it. And she lives in Austin. She was using it in Austin traffic. Austin is like, it's the construction apocalypse there on the highways for the last several years. So the construction was constantly freaking out my sister. And just at the point when she got used to using it in traffic, they activated the cut-in, right? And all of a sudden, she was getting all of the what she thought was shadow braking, the car responding to imaginary things. Well, they turned on cut-ins so that the car would slow down and move to try to avoid cut-ins. And of course, she had a certain false positive rate when they first turned that on.
Right.
And it completely wigged my sister out for like 3 months. She didn't want to use it because her confidence in the vehicle's ability to. But anyway, so working through that with her, I was really sensitive to the rate at which the cut-in detector improved, and it was very satisfying to see the cars have no cut-in detection ability. Then it would turn on and they had a false positive rate that was pretty high. Like on any given drive, if I drove, 5 minutes or 10 minutes on the freeway here in Los Angeles, with typical LA traffic on it, like it'd have 3 or 4 false positives, right? And then it went from the false positive rate fell by like a factor 100 over a span of 2 weeks. And then maybe another factor 100 after that. And now it's, it took them a month or two to get it to where it was essentially perfect.
Okay. So I had a different perception of shadow mode, and Jim Whitehead, one of the moderators of the chat, sort of asked, I'm going to ask it my way, or I'll say it my way. My impression was that when you're driving the car, like it's not an autopilot, it's not an FSD, I'm driving the car. FSD is still identifying objects. It is still predicting paths. It is still assigning probability vectors. And if it sees flicker on an object, that's something that it can train on. If something moves outside of the probability vector prediction, then that's something it can train on. So a question I guess I basically had was, is that not shadow mode?
You could, sure. I think that fits the general definition.
Okay.
So
I guess let me phrase.
AP always, if you have AP in your car, every time your car is on, AP is running. It might not be taking control of the car, but it's trying to drive. It's just not being allowed to drive the car. And so all of the behavior that the system engages in is detectable, evaluable, and reportable back to Tesla. So if you're driving the car, AP is, it's running and it's producing useful data for Tesla. Obviously it can't be looking for, there are all kinds of things that it can't detect if the user is driving the car, right? But there are lots of things that it can, and it does.
And then, like, if you drive differently than it would have driven, like if you go through an intersection differently than the way it would have gone through the intersection, that also might be a trigger that it learns from. So the question I sort of had was, does FSD learn, like speaking specifically of this shadow mode, that the human is driving, the vehicle is identifying objects, predicting paths, predicting where you're going to go, does it learn as much in that mode than it does does it learn as much in that mode as it does when it's driving itself?
It learns some things, it learns better, and some things it doesn't learn as well. So when we were talking about this, what lane will the human take thing when you're trying to figure out how to transition. Okay, when autopilot is driving, you can't do that trick, right? Because autopilot is choosing the lane across, so you don't get to evaluate. So that's an example of something it can't do as well if autopilot is driving. But then there are other things, for instance, how did I do on the cut-in detector, right? So with the cut-in detector, you can look at whether the car moved or not, but did I do the cut-in braking smoothly or not? That's a thing you can't evaluate until the car takes it over, and you look to see how drivers respond to it, right? So there are situations, there's some kinds of things that AP has to be running for you to get feedback. There are other kinds of things where it cannot be running if you're going to get feedback. And then there are some things that work both ways. Like a lot of the neural network evaluation object, like the flicker detection, it can do that whether AP is running or not, because the neural networks are always running in the car.
I had this conversation with someone, and they said that the car uploads a lot more after the car was driving than the car uploads when I was driving. Do you ever like measured that? Have you ever noticed that?
I know some people who track that pretty closely, and over time it's been all over the map. Tesla will push a set of triggers out to the field. Like, here's a bunch of stuff we're looking for. And if you see it, give us this information back. And sometimes the information they want back is really small. It's just a snapshot. Like, we need more pictures of garages. If you see a garage that has these characteristics, take a picture and send it back to me. Those aren't very big, right? But sometimes there will be the, like, the lane, the intersection traversal thing. You might imagine that they could push a trigger out to the car, which tells the car, if the human is driving and they drive through the intersection and they pick a different lane than you chose, like you predict the lane they're going to take, they pick the lane. If only in the case in which the lane they go into is not the lane you predicted, I want you to save 20 seconds of video from all the cameras and give me all that.
Right.
So if you have that trigger running on your car and you drive manually through the city, right? And if you're the kind of person who changes lanes in an intersection, your car is going to upload a ton of data when you get back to the garage, right? Because they're running that trigger on your car.
Right. Okay. I wanted to turn to something different. I mentioned this to you before we went live. Elon talked about becoming an AI, like a third part of the company is an AI robotics company. And I think this is something that he'll address more at an AI day if the AI day actually materializes. He said robotic. Like, the AI didn't surprise anyone because they're doing a lot of AI. He's talked about AI. But when he said robotics, I was like, what? Because, the cars are robots. But, he's talked about that Tesla, the FSD project is basically solving a lot of real world AI. So I have one specific one I mentioned to you, but do you have a sense of what kind of robots might be really, like what other robots might Tesla develop using this technology?
Well, I think I would love it if they would develop a general purpose humanoid robot. So that's a benchmark that I use for talking about robotics a lot, because it was so. If you can adapt the environment to your robot doesn't have to be very smart, and you don't need AI, right? The more your robot has to adapt to the environment and the more complicated the robot is, the more you need AI to be part of the solution for that robot. So like factory robots, they have a totally constrained environment. They don't need any AI at all. Drones, they need a certain amount of AI today, the way that they get used. If you've used recent generations of consumer drones, they're definitely putting a certain amount of AI into them, because a drone has to accommodate its environment. You don't put the trees where it's convenient for your drone. Your drone has to fly in a way that's convenient for the trees that you have.
You don't set the wind to be appropriate for the drone either, right?
Right. The drone has to accommodate its environment to the best that it can. So when you look at the spectrum of all the different things you could use robots, in the world, one of the axes rated on is how simple is the environment and how much can the environment be adapted to the robot. And at one extreme of that, which is, I think, a very commercially interesting application, is there are all these things in the world that are designed for human beings, right? Doorknobs, kitchen utilities, washer and dryer, a car, the boxes that we carry around, like all the hand tools, the portals, so much of the infrastructure of the world that we live in is designed to accommodate a human being, which is, a creature that is, about this high, that weighs about what I do, that has about the same physical strength that I do, that has about the same dexterity, that moves at approximately the same speed, that has the same set of perceptions and reaction time and that kind of stuff, right? So there's a ton of useful, like if you can build a creature that drops in that spot, that has essentially the same gross set of characteristics, that one creature could, that one, I'm calling it a creature, that one mechanism, it has a lot of applications that you could immediately drop it into if you could build that thing. But the flip side is, we're not going to adapt the environment. Like the benefit of being able to build a humanoid robot, and there are lots of other useful things. This is just like, call it a thought experiment, right? The benefit of having a humanoid robot is that that if you've got one, there are so many things you could immediately use it for. But the flip side of that is that we're not going to adapt all of those things to suit the robot. Not much of it anyway, right? We're not going to change all the elevator buttons in the world so that they're robot compatible, right? We're not going to change all the doorknobs. We're not going to change all the hammers, right? These things are all things that are built for people. So if you want the robot, if the robot is a physical adaptation, if the body of the robot is a physical adaptation to fit the economic niche that the human body is performing in right now, you have to provide the kind of perception, the ability to navigate in the world, to plan and whatnot, that's on a scale that human beings have. And that's an AI problem, right?
Right.
That's kind of an extreme example. So could they do that? If they could do that, that's kind of the net plus ultra of basic robot concepts in terms of the amount of utility that you could get. But it's also an extraordinarily difficult problem. That problem has a lot in common with the autopilot problem. Now, the environments that a robot has to navigate are more complicated. The planning, the rules, there's a lot of stuff which is more difficult. Some things are simpler, like a robot can walk slower because there's not going to be a line of robots or a line of people behind them waiting for them. Like, if your robot takes 3 hours to mow the front yard, you probably don't care. Right. It's not that big a deal as long as I don't have to do it and it gets done right. That could be okay. Right. But it is a very complicated problem. And the one of the things that I think is really interesting about what Tesla is doing with autopilot is not just the development of autopilot itself or the economic benefits it proves. While those things are very significant, and even by themselves, they're more than enough reason to do that thing. But Tesla is also pioneering a process for rapidly developing an extraordinarily sophisticated AI stack for controlling, a sophisticated object in the real world that human beings inhabit, right? It's really complicated, where actions have consequences, and there's this very long tail of weird things that you have to be able to deal with. So I think that's a really interesting example. So you mentioned a roofing robot.
Yeah. So
a roofing robot kind of occupies a space that's between these two, right? That roofs are much more constrained than every sidewalk and hallway and the environment that you have to move in. Also, the things that the roofing robot has to deal with might be a small subset of all the things a human might do. You can use a staple gun to attach things. It only has to be able to recognize a certain set of objects and whatnot.
I would say humanoid form might not be ideal for a roofing robot.
Yeah, and it wouldn't be.
Right. But I think a spider bot
have 4 legs. So it's stable on a roof.
I was thinking
spider. You don't want something that stands on 2 legs.
Spider bot, so it can even climb the house or just climbs the ladder better. But my pitch for a roofing robot is, number one, Tesla has a problem getting roofs installed, and if you could, and roofing is dangerous. Roofing is one of the most dangerous occupations in the world. And I don't know if you know my history. I'm a personal injury lawyer. I'm a personal injury criminal defense lawyer. I'm mostly retired from all legal work. I no longer have any personal injury cases, but I know from my work, falling off roofs is really dangerous. Like, you probably know that.
A roofing robot, it could stand on the ground if you just make it tall enough that it just leans over.
Well, one theory is it stands up, but the thought is just plain and simple. If you can offload some of the work that humans are doing so that the robot's doing it instead, then you're saving lives. Like, if you take half the work that humans are doing on the roof, you're taking jobs away. This is one of the things that people hate, is you're taking jobs away from humans. But I would rather take the dangerous jobs away from humans if I could. Like, lawn mowing isn't particularly dangerous. Sometimes lawn mowing can be dangerous if you stick your hand under it. But generally speaking, lawn mowing, as long as you're somewhat careful, is not that dangerous. But roofing is very dangerous. So people who don't know this, if you fall from 10 feet, there's a decent chance you're going to break a bone. If you fall from 20 feet, there's a decent chance you're going to die. If you fall from 30 feet, there's a very high chance that you're going to die. And some of our roofs are 20, 30 feet high. So if we could replace half of the human labor with robots doing half of that work, then we're going to save half of the lives of roofers, right? So, and I like what you're saying, that it's a constrained environment. You don't have to learn everything. The space that you're dealing with, that the robot is dealing with, is a lot more constrained. It doesn't have to worry about traffic lights. It doesn't have to worry about, it's kind of a 3D space more. The driving is more of a 2D space, and roofing is a little bit more of a 3D space, I would say. Is that fair? Or is driving? because you're
I don't know. I would say on the roofing robot thing that that the software problem of the roofing robot is probably not complicated enough to be worthy of an AI day kind of presentation. I mean, I wouldn't be surprised if Tesla has a lot of clever ideas about how to streamline and improve the safety of roofing, and maybe that will manifest in a roofing robot. That would be great if they did that. But I wouldn't see. It's a bit too constrained to really be worthy of artificial. Like doing it with a drone is tougher. Like perceiving the real world and dealing with highly variable situations where you don't have an opportunity to recode the robot in order to adapt the environment to the characteristics of the robot before you put the robot into action. Those are when you can't do that, that's when you start really needing to use what we would reasonably call AI today. AI is a moving target, right?
Right.
It's like we keep redefining the term. Every time the machines get any better, we say, well, that's not AI.
Right. Well, no. So you mentioned drones. Drones is actually something I'm kind of fascinated by. Do you follow Kathy Wood and ArcInvest and their reports?
Some of it. Yeah.
They had a PDF. I think it was their Big Ideas PDF for 2021. Mm-hmm. And so there's this question that I've been talking with people about, and I've kind of come down on ArcInvest's side on this one. I originally thought that robo-taxis would be better for delivery than drones. And the idea would be, you run a pizza place and you put, a couple pizzas in the car, and the car drives to a few homes, and you tell the people come out to the driveway, or maybe you have a robot in the car that brings the pizza to the front door, one way or the other. And I thought that was a better solution than drones. And maybe pizza is a bad example. I'm not sure. Pizza might still be a good example. But I read this research article, and I hadn't really thought this through. But the drone, with the robotaxi, you've got, let's say, 1,000 kilograms of mass. The robotaxi itself, the packages that you're delivering with the robotaxi are fairly trivial in mass compared to the robotaxi. So you've got to move this robotaxi from point A to point B. It probably has to take a slightly longer route than a drone would have to take, but I don't think that's a big deal. It's just you've got to move. If you've got a 5 kilogram package you're trying to deliver, you've got to move 1,000 kilograms plus 5 kilograms from the place it's coming from to the place it's going to and back. If you do it with a drone that weighs 20 pounds and it's carrying a 5-pound package, then you only have to move 20 kilograms and 5 kilograms. Then you only have to move 25 kilograms. So I think that the flying drone ends up being, even though flying might be a more energy-intensive activity than driving, because you have to stay up, I think the drones might actually be far more efficient. The number I saw in this research paper was like a 5-mile each way round trip, so 10 miles total. The drone only costs like 10 cents to do that delivery. So I think we may enter a world where, like my original thought that robo-taxis would be making these deliveries is probably wrong. That you're going to have flying drones making a lot of deliveries. What's your thought on the car robo-taxi delivery versus the flying drone delivery?
It's both arguments have. There's a so this is a good. This is actually a good topic to talk about, whether the world has to adapt to your solution or whether your solution is adapting to the world that it is right now.
Yes.
Right. So flying drones are great for the situations that so if you've got a light package and you're talking about a service where you really want the delivery time to be short, if it's a pizza or your Starbucks coffee, that kind of thing, there's a big premium on not getting it tomorrow or not getting it in 3 hours or getting it in 15 minutes, right? If the package gets heavier, right, then the dynamics start to change a little bit. But here's the thing that's really important. The space of addresses that you can directly access with a flying drone is actually very restricted. Now, it's less restricted in suburban America than it is in a lot of the world, but a huge chunk of the population lives in cities. You live in a high rise, how are you going to deliver Starbucks coffee to somebody, on the 22nd floor of a high rise?
Can I push back against you with that? What if the high rise has patios?
So maybe it does have patios.
If it has patios, the drone might actually be better at delivering than the vehicle.
Sometimes, right? Yeah, as long as the wind isn't blowing too hard and it's not raining super hard, you know. Yeah, I mean, there are high rises that it's going to work for, and there are high rises that will adapt, right? You could imagine a high rise putting a drone port on the roof, you know,
Oh, I love it.
where you can drop stuff off. So, but once again, the world has to accommodate your solution. So this is the opposite extreme, you know. If you're a humanoid robot, any place a human being can go, it can deliver a package, right? So the drone works great where the drone works.
Yeah.
But there's a very important space of things that the drone can't do. And the thing about the humanoid robot is that it can do all of those things. It can press elevator buttons. It can open doors. It can walk up flights of stairs. It can get in an elevator. It can do whatever it needs to do to deliver to all the infrastructure that the world has today, right now, as it is. So if you have the humanoid robot, it immediately can attack all of these problems. I'm not saying this is trivial. The drone is a much simpler problem to solve, right? And there's a very useful space of problems it does solve, especially since, you know, the most unserved, the parts of the world that need that have inadequate delivery service right now are by and large amenable to flying. Like people who live way out in the boonies, right? Or you know, people where there's a winding road up to their house or whatnot, stuff like that, which is difficult, or who live in a gated community that UPS doesn't like to deliver to because it takes forever to get in, or whatever the deal is. I mean, drones can deal with a bunch of those problems, but the humanoid robot is omnipotent, right? Once you have that, it can deliver refrigerators. It can deliver your couch, right? It can also deliver your Starbucks. And also, I would push back a little bit on the energy thing. It is certainly true that the cost, the incremental cost of delivering a cup of Starbucks coffee, if you're flying a drone, if you can deliver it with the drone, it's going to be a lot cheaper than the humanoid robot is, right? But you know, if you've got a $10,000 chassis on a humanoid robot and it's running advanced software and that kind of stuff, what does the electricity to deliver a Starbucks a cup of coffee cost, right? Robot gets on a scooter, goes to the address, walks up, it's 15 cents of electricity either way.
If the robot is riding, so my theory was that the battle is between flying drone and Tesla 2023 compact robotaxi or Tesla or Model 3 doing deliveries. And once you get to heavy packages, the flying drone doesn't work as well. I think we can agree on that. If you're delivering a 50-pound package, it's a lot harder for a drone to do it and a lot easier for the car / and I think the idea is the robot's in the car, right? The car drives to, but you're saying you don't even need the car anymore. The robot rides some.
The robot can be on roller skates.
The robot's on skates or something. Yeah, I hadn't thought of that. That
it's the robot's time isn't important, right? We don't care if it takes 20 minutes to get someplace and it can only go 30 miles an hour or whatever the deal is, right?
Right. That's a bigger thing.
And electricity is not super. I mean, a humanoid robot has energy efficiency that's roughly comparable to a human being. So, what's the cost of the energy that we put into a human being to go do one of these things? It's not trivial, and the drone is definitely lower, but it's not the component. It's given the choice between, paying 10 times as much for the electricity, but being able to go anywhere. Or paying 10 times less for the electricity and only being able to address, go to like 20% of addresses, right? Which is the better business opportunity.
Interesting. All right. So I am through my outline. Is there, and we are 2 hours and 25 minutes in. You've given me a lot of your time. I really appreciate it. Is there anything you wanted to talk about after all we've talked about? Is there anything that pops in your head from all this that I missed or...
I love to talk, and I can talk about all kinds of things, but that doesn't narrow it down.
Okay. So
maybe we can have another conversation. We didn't talk about Tesla's business prospects at all, which I think is kind of interesting. But that might be me listening to you more than you listening to me. But
well, here's a question. I wanted to give the audience a chance to ask questions, so I have a question from Romu. Could humanoid robots be trained for tasks by human workers gathering data for the system by wearing smart glasses? Is that potentially part of the training process for the AI?
It could be. Because
you're talking more about generally understanding the world, not training for tasks, right? That's my understanding of your take on it.
Perception is a really big important of the whole. I mean, actually, planning is much more complicated for robots than it is for cars. just because the space of possible ways to accomplish a particular objective can be much, much larger. Like a robot wants to make an espresso for you with the espresso machine in your house, right? The space of possible ways it could go about doing that is actually quite a bit larger than the space of possible ways that your car can drive up the street and enter your driveway, right? The planning space is a lot more complicated.
Wait. Explain that. Why is making an espresso more complicated than driving from point A to point B? Maybe I don't know enough about espresso.
Well, yeah, it's, there's 5 things you do, and you can do them in different orders, right? So planning involves exploring the planning tree for making an espresso might involve, you've got several decision points, and you might want to explore that whole tree in order to evaluate something. That's not how neural networks do planning, but that in the classic planning space it is. But the thing is, for the car coming up the street at any given point in time, it knows, that point ahead of me, 10 feet ahead, that's the next thing I'm going to do.
Right.
It doesn't have a lot of decision trees. It only has a decision tree when something's blocking its path that it has to deal with, right? So, and that's not really a planning function, right? That's just it's a behavior movement constraint or whatever the deal is. So that's why I was saying, like, planning for making espresso or making coffee or walking across someone's yard, if they have a dog, like, how do you deal with a dog if you're a robot might be a complicated planning. Like, is it a big dog, a small dog? Is it barking? Is it on a tether or is it not on a tether? Is there a sign that says don't enter the yard, right? Is somebody standing on the porch yelling at you? There are all these things that you potentially might have to take into account that the car doesn't really have to.
That was actually a question that somebody asked earlier that I meant to ask you is, does Tesla FSD have hearing? Does it hear the environment at all? Is that an input?
I believe that there are microphones in the car. Yeah, actually, there's interior microphones for sure that that the MCU has access to and could provide to.
Like siren, yeah, like if it hears a siren, it can hear a siren? To the best of
my knowledge, there's no external microphone on the car, but there is an internal microphone that can hear whatever the driver hears. So if the driver can hear a siren, the internal microphone in the car could hear a siren.
Okay, so there was a question. I got some questions now. It's an interesting question. How can FSD win hearts and minds? What do you think Tesla could? Because you and I are probably just like excited about Tesla's autopilot, FSD, whatever. There's a lot of people out there who might not get it or might be afraid of it. Can you think of anything that, like, the questioner suggested, like a self-driving car motor, racing content, racing series or something?
PR-wise.
Do you have a sense of something that Tesla or the self-driving car community could do to win over people who are skeptical or scared?
I think the best thing Tesla can do is make a good product. In the long run, I think that wins. That right now, I mean, my impression of the landscape of winning hearts and minds right now is that it's massively complicated by the super toxic, relationship that Tesla has with the media. And incidentally, I place the blame for this on the media, however I happen to have phrased it. Right. And that's just really unfortunate that Tesla is it's the be all end all of clickbait today. And that leads to really unfortunate, and media, if it bleeds, it leads, right? They like to go with negative stuff, and that. Yeah. So we've got this very unfortunate dynamic, which is probably going to have an outsized influence. I want to get my dad into a Model Y, and I really want it. He's over 80 now. His window of being able to safely drive the car that he uses for so much. He lives in Iowa, right? That's not a place that you can get by without having a vehicle. If you live in suburban Iowa, I want to get him in a Tesla, and I want him using FSD before he gets to a point where he has to make a decision about driving safely versus being able to go where he wants to go. And but his impression of FSD is like what Fox News tells him about it, right? Which is not really glowing reviews, or what Consumer Report says. And all of these things are just wrong. They're false. And I have other people I've put in Teslas. I have other relatives that they had a learning curve to get over it. experience with people using FSD is that people who embrace it and spend some time with it love it, right?
Yeah.
They come to love it. And so in that sense, the it makes people into believers, when you use
Right.
it. The thing is, it's a different way, it's a different relationship with a car, right? And
Right.
so it requires a change in your expectations and a change in the way that you use it. Once you make that adaptation, it becomes an irreplaceable part of having a car. Like, I don't know anybody who has AP and has used it and gotten over the hump and has a good relationship with it, who ever wants to have a car that doesn't have it again. Like, it's a necessary part of a car to people
Right.
who like. So I feel like the product can do that, but I don't know what to do about this situation with the media. Like, I like, until mainstream media has finished imploding from their encounter with social media, I don't know, you
Right.
know
I don't think
where
I don't
does
think
this
the media is
end? God, it's
I don't think the
scary.
media is winning. I think the media is persuading a small segment of the population. A large segment of the population isn't paying attention.
Well, they're
And
not.
another
They're
yeah.
dying, right? I
Yeah.
mean, these are the death throes of an industry that we're observing
Yeah.
here, and I don't know what comes out the other end
Right.
I could rant about the media.
Okay.
Media was tabloid forever, right? We only had this tiny window of time from the 1950s or 60s up until maybe the 1980s, where the public kind of thought of the media as as like, higher on the ethical totem pole than, like, lawyers and con artists and that kind of stuff. I
Yeah,
mean,
yeah.
that was how we
Car
thought about
salesman.
them for a long
Yeah.
time, right? And
Yeah.
and somehow, Walter Cronkite changed all that, and Dan
Yeah.
Rather, and now the media is back to, where they were back in the 20s. And
Yeah.
so it may be that this is the natural state of media, and we're just going to have to get used to the fact that
Right.
that it's that the inquirer is the rule and not the exception, right?
Right. So there's a question here that I get a lot that I think is a really good question for you, and I have my own answer to it. Skimning asks, how will humans earn money when all labor is made obsolete by robots and automation? I have my own answer to that, but I'll let you go first.
Well, the answer. So the answer I really believe is not something I can explain in like 5 or 10 minutes, unfortunately. Let's see if I can come up with a good summary for it.
Should I give my answer first, and you can tell me what you think of my answer?
Go ahead. Yeah.
So my answer is that that is a massive underestimation of humans, that humans have a tremendous neuroplasticity. We have had massive wrenching technological change for more than 100 years that has radically altered what people do for a living. And every technological advancement ends up creating more jobs and better jobs than existed before the technological advancement. I see no reason for that to change. So, and my favorite example, this is the automated teller machine. Everyone thought all the bank teller jobs would be wiped out by the automated teller machine. And the ATM made banks so much more efficient that they were able to open more branches, and it freed up the tellers to do more valuable work, and it actually doubled the number of automated teller jobs. Doubled the number of regular bank teller jobs. And it still has not declined below where it was when ATM started. We are seeing some changes that online banking is eliminating some of the work that bank tellers did. Not ATMs, right? Online banking.
Mm-hmm.
So that's my take on it, is people massively underestimate humans. We are adaptable. We will find something to do. There will always be something for us to do.
Yeah. There's a lot of merit to that perspective. A lot of people share that perspective, and I think it's got a lot of validity to it. I think the world is not the economic world is not exactly what we have a framework for perceiving how economics of the world, but earning a living and being productive are kind of two different things, right? Earning a living is more about, how do I get my slice of the bounty that human industry creates. So human industry clearly provides enough to provide for the basics for everybody that's alive, right? And we have distributional mechanisms that are imperfect, pretty good most places, but imperfect. So so part of the question is, like, how do people continue to find value in themselves and have useful things to do with the hours of their day, right? And then there's being productive, right? I think being productive actually gets more, in some ways, it gets easier when you have AI, because AI is like, it's better tools, and AI is a tool to a human being that really wants to accomplish an objective. I mean, you think about is an AI going to replace Elon Musk? Well, if an AI can do everything Elon does today, Elon will move on to doing something else, and he'll use the AI to further his goals, whatever it is. And people who take that attitude are going to become more productive, right?
Yeah.
But people who, you can see an alternate thing where, there's this thing I want to do and I like doing it and I derive value from it because I can do it and nobody else can do it, or I can do it better than other things. Well, when the AIs are doing it all better, there's going to be a component of things people just don't feel like doing anymore, right?
Right.
I think the motivation for becoming a chess grandmaster is a little different now than it was when chess was perceived as the ne plus ultra of intelligence, right?
Or now Go.
Once it's
or now the game Go.
Once your phone can kick your ass, there are things that just aren't very interesting anymore, right?
Yeah. So the other thing I would just say really quickly about this before I go on, we have a question I want from Neuropod. There's a concept in economics called the law of comparative advantage. So you have a country like the United States is basically more productive at everything than Botswana. I'm going to pick a random African country, or Venezuela. You pick whatever country you want. There are countries that are very unproductive, and the United States is highly productive, or China is highly productive. And despite that, the law of comparative advantage says there's always something for the unproductive country to do, because although we're more productive in an absolute sense at everything, there's some things that this country is relatively more productive at than we are. Like there are certain things they're relatively good at compared to the other things that they do. And so they do the things that they're relatively good at. And the way the law of comparative advantage works, if you go through the economics, you go through the math, basically, it obviously makes sense. If they produce nothing and we produce everything, well, then we produce less than if they produced something. So there's some value in them producing the thing that they're good at and then trading for the thing they're not good at in a relative sense. So that's sort of another answer. But Neuropod had this question. Says, and thank you for your support, Neuropod. This is I think this is Ryan Tanaka. He has it's a channel on YouTube, Neuropod Neuralink. He says, James, which Elon company are you most excited about?
I guess I'd have to have a time frame to be excited over. I'm super excited about Tesla. I think Tesla is, my focus on Tesla has always been about automating driving, right? And I see that as, over the next 10 or 20 years, a super impactful thing that Tesla can do that's going to make the world a lot better. The EV thing, I'm pretty excited about too. I worked at an EV company. I designed stuff that went into EVs for a while. But my experience working at EV companies in the 90s was that EVs are hard, right?
Yeah.
And even though they're a great solution for an enormous number of things, like the risk-adjusted rate of return on investment there was unfortunately really low because the risk was so high.
Yeah.
It's great. I think Tesla's going to succeed there, and I think that's great. There are other timeframes where I think that SpaceX is super exciting, kind of this medium turnaround. If I have to say, in the long run, like what really moves the dial? Like what's the thing that changes the nature of human existence? Well, yeah, that's Neuralink, right?
Yeah.
It's just like long term in terms of the potential for changing the human experience. Like, there's nothing that compares to Neuralink. Scaled up, if they achieve their ambition, it completely redefines what it means to be human.
Okay, there's a question. This is a while ago, but there's a question from Edward. I'm going to rephrase the question. What do you think about LiDAR for self-driving cars?
I think that it's super useful for getting your demo out. That it is, right? There's a space of things that are important to self-driving that are dramatically easier if you put LiDAR on your car. So that's my number one. So I also worked in the optics industry. Like I developed nonlinear optics for a while.
Yeah.
I've been skeptical about the. So LiDAR is it's a single word, but LiDAR sensors themselves, they come in a huge spectrum of capabilities, right? There's how many lines you have, what's the resolution, what's the range, what's the update rate, what spectrum are you operating in? Like all these things change the characteristics of a LiDAR. Having a LiDAR which does all the things that ideally you want a LiDAR in a vehicle to do is very difficult to make inexpensive with any technology which is well understood to be production worthy today. Now, that doesn't mean it's never going to happen. It's just the development cycle on this is a lot longer than the optimists in the space would like it to be. So I think it's going to be a while before LiDAR, which is meaningfully better than radar, right? I mean, because radar can do a lot of the things LiDAR does. But if you're going to build a LiDAR that is meaningfully better than a $100 radar, a $200 radar, it's going to be a while before that LiDAR is inexpensive enough that it's a gimme that you can toss on a car. And there are all of these other constraints too. There are optical limitations to what you can put on the fascia for that, and then designing it into a vehicle is kind of challenging and whatnot. So I have a hard time imagining LiDAR being used in a general solution for a consumer vehicle that goes out the door. In a robotaxi, I think you can do it. Like the economics for using LiDAR on robotaxi, like robotaxis potentially make so much money that you can afford an expensive platform, right? And so like Waymo can put their they can put several $8,000 LiDARs on their platform, and they can still have an economically viable taxi today, when the competition is human-driven cars, and when the unmet need is very, very large compared to the capacity that any of these networks are going to have in the near term.
Yeah.
So,
okay, I'm gonna
in that sense, I think LiDAR's got its space. It can function for a while. In the long run, I don't think you see any of these systems with LiDAR on it. It's, as I mentioned, multispectral cameras, thermal. I mean, there's 20 other. Why are we talking about LiDAR? Like, why is LiDAR the thing that so many companies want to hang their hat on? And the reason is because during the DARPA Grand Challenge, the guys that put LiDAR on their vehicles succeeded, and the ones that didn't, they failed. Right? We saw this existence proof that LiDAR in a certain space, it works really well.
So this is actually going to come back to the Tesla. Elon's talk about dropping radar. Does LiDAR help the software understand the world better?
Yeah.
Okay, because the question I had, the thinking I had was that in the world of machine learning, we have this really well-developed community that's trying to solve the vision problem with images, right? You show a bunch of images to you tell it this is a cat, this is a cat, this is a cat. You show it 100 pictures of a cat. At some point, it figures out what a cat is. I don't think that same approach applies to, like, LiDAR doesn't identify objects. LiDAR identifies distance, and maybe it identifies velocity if it's got, like, using the Doppler effect, right?
Well, strictly speaking, cameras don't identify. Is it like the comparison is not between LiDAR and a camera with a neural network, right?
Okay.
It's a LiDAR and a camera, or a LiDAR with a neural network and a camera and a neural network. So within the space of plausible perception that a LiDAR provides, a LiDAR can recognize objects. Like, people have done this many times.
Okay, so
they build pure LiDAR systems.
LiDAR can identify an object.
Yeah, but I mean, it can't tell you what color the object is,
right?
And it can't tell a trailer hitch from a pigeon, right? Okay. So that's a problem. But it can identify that there are things that cameras can't disambiguate very easily either. Like a camera can't tell a warm object from a cold object because it's outside the space of things that it detects. LiDAR is without exception used in conjunction with cameras to solve this problem. So LiDAR isn't used to recognize objects. LiDAR is used to provide an additional dimension of data to the same neural network that is consuming camera inputs to assist the neural network in understanding the camera input that it sees. Right. That's what LiDAR does.
So nobody's talking about using LiDAR.
That's what LiDAR does for neural networks and object recognition. most of what LiDAR does in self-driving cars these days is precision localization, which is a completely different thing.
Right. But so no one's talking about using LiDAR alone. It's got to be LiDAR plus cameras plus.
Oh yeah.
Okay. So
no, it's not even on paper, you can't solve the problem without cameras.
Right, so,
you can't. I mean, the driving system is designed to be solved by people with their eyes, right? I mean, our whole driving system is designed around that. You can't, like, what are the odds that you can put a blind guy in a car and you're going to get a good result, right, of him driving? Like, what do you have to add to the blind guy? No, seriously, just think about it this way. I've got a blind guy in a car. What can I give the blind guy? Like, there are going to be no cameras on the car. Right? How is a blind guy going to be able to drive the car? And the answer is that is not worth solving. Right? That is such a hard problem. It is not worth solving. And yet, because the system is designed to work with vision, how do you tell a green light from a red light if you don't have vision, right?
Okay, so just along those lines, though, Karpathy has talked about this. I think you've talked about this. There's this concept called Pseudo Lidar, where you're basically using the cameras and you're able to effectively generate the same information that LiDAR would have generated if you had it, without even needing to have the LiDAR. How effective is, first of all, am I correct? And second of all, how effective is Pseudo Lidar, if I am correct?
Yeah, I've been meaning to replicate those research results because I would like to get better. So I hadn't heard of this piece of work until Karpathy mentioned it in a talk, and then I went looking for, like, who else used that term, and I found the research paper. It has a lot in common with things I've seen in the code and things that Andre said. So I believe that I identified the research paper that is probably the root of the way of the term as Andre is using it and the way that Tesla is using it. So Pseudo Lidar, the way that it's used in this paper, it's a machine learning paper, and it refers to a technique by which you can use just cameras to achieve object recognition performance, which is comparable to what LiDAR plus cameras normally get. So this is a way of essentially using a single camera or using a pair of cameras to achieve comparable results to what normally you would use LiDAR along with a camera to do. And one of the exciting things about this is that there is a self-supervised learning component of this, which makes it reasonable to do in production today. It's not just a research problem. I mean, these folks, they identified a technique and a mechanism for doing this. And then Andre actually talked in more detail about how Tesla was doing their depth recognition, and he emphasized this was a response to a question about self-supervised learning to him, if I remember the dialogue correctly. But anyway, if Tesla is using self-supervised learning to do these techniques, and they're applying them in the same way that the Pseudo Lidar paper applied them, then what they're getting out of it is object recognition. There's certain types of object recognition problems where depth is a constraining factor in your ability to get good results. And like an example of this is, I'm looking down a road and there's, I see a car coming and there's another car behind the car. I want to see the car behind the car, and I want to identify its distance and speed and those kinds of things. So it's occluded by the car that's in front, and I can just see the side of it. So it turns out that if I have a depth map of the space, right, that is, I know what the distance is for each of these pixels, or on some grid of this, I know what the range is to the nearest object in that space. It turns out that if you have that input, which is essentially what LiDAR produces, you have much higher accuracy on identifying the car behind the car where you can just see the edge of it, right? Because that depth map helps you understand that, you have an object, and then you have a space, and you have another object behind it, and that object it's separate from the background, and so on, right? I mean, especially in certain lighting conditions that can happen. So what you want to be able to do is independent of, without having to have a separate sensor modality, sort of understand the depth map of of what you're looking at. And it turns out that pseudo lidar is a technique for specifically training that ability into a neural network, which does not require that human beings label images to train it. It's a mechanism where you can take a bunch of sensors out into the world, you drive them around, you grab a bunch of data, you dump that into a computer, and it cranks on it back and forth, and it dumps out a set of outputs that you can use for training the neural network to do this trick. So Andre showed the output of the depth network that they've got. I've seen the depth network. I know they have depth networks in their system. Depth is an output that comes out of their neural networks, some of them right now. And he, in one of his talks, he showed what their depth output maps look like, and they look really good. Now, he might have been cherry picking those examples. I only saw 3 or 4 of them, but they looked great. Right. And if they're getting depth maps that are that as good as what he was showing, like if that's a typical depth map, then they don't need LiDAR.
Right.
LiDAR's got nothing to offer them at that point.
Okay. So I have a thank you, Noah Jones, for your support. Noah says, and I don't know if you're going to get this because I don't understand it. He said, brain ship of Theseus, neural lace as new planks. Do you know what that's about? Brain ship of Theseus, neural lace as new planks. I don't understand if that's a question, I don't understand it.
Spelled?
Planks.
Neural lace, huh?
All right, so
I mean, I know I get the neural lace reference. Because
you've read
it sounds like it's a reference to a book that I haven't
You've read the Culture series, or you haven't read the Culture series?
Yeah, I've read it.
Okay, because the neural lace, for those who don't know, neural lace is a concept that's in Ian Banks' The Culture series, supposedly one of Elon's favorite series of novels, which is basically, people think that's where Neuralink came from, where the idea for neural. So there's another.
Well, no, Elon referenced neural lace, and he used before Neuralink was created. He talked about the idea of brain-machine interfaces. He referenced the neural lace concept, and he, in fact, described a potential way of implementing neural lace, which is not what they're doing with Neuralink, which is derivative of the way neural lace is described in those in those. And other people have talked about doing neural laces too, which are introduced in the brain via the vasculature.
Okay.
Right. The vasculature of the brain. A great thing about the vascular infrastructure of the
blood
brain,
vessels,
right, is that you can get access to the whole brain through the vasculature. Like if you build a very, very small structure which can weave its way down capillaries inside the brain, it's a minimally invasive way of getting access to like all the tissue in your brain, right? But so it's super exciting. Of course, that's not what Neuralink is doing.
Okay. So Aptera Reboot, thank you for your support, says, seems the in-vehicle hard software works on WWDD. What would Dojo do? Wouldn't vehicles need at least some onboard training hardware software which queries Dojo network for true Turing level AI? Thoughts? Do you think that the vehicles need to be able to query Dojo as it's driving? Does it need to? Go ahead. Sorry.
The conception for how the system is architected today, it does not have that sort of it doesn't require access to the cloud or anything. The vehicle, when it's driving right now, is completely
self-contained. I guess the question is, for it to be truly that good, does it need to be able to query the data center or the Dojo as it's driving? Or is that not, ultimately, is that going to be something that's necessary to make the car drive well enough to be good enough?
The car will get superhuman without, the platform that they have right now, they can get to superhuman by any reasonable definition of superhuman. There are, things that, will it be able to compose poetry? Maybe not. There will be things humans are still doing that autopilot isn't doing for a while. But as far as the basic function of driving, it should be able to get there. We don't know how complicated the problem of driving is, right? Human beings do all kinds of things that we don't understand the complexity of, because we don't understand what goes on inside people's brains. We have no way of, from an information theory standpoint, evaluating the complexity of the computational processes that are engaged in the human brain while you're driving a car. Right. And we haven't built any other system that can drive the car. So we don't know, we can't set a lower bound on the complexity required to drive a car with the same proficiency that human beings have. It feels like we're getting really close. You can look at the trajectory of improvement and the amount of training that gets done and the computation, and it really looks like we're going to hit that intercept, right? But we don't know absolutely what the shape of the curve is between where we are right now and when we cross that threshold where any reasonable person will argue. We don't have metrics. We don't have really good objective metrics other than accident rates for evaluating, how this stuff works. So to some extent, we're not going to know until we get there when the car is superhuman, like when you could reasonably say that it's superhuman. And that's the biggest unknown.
Yeah.
Right, is that we don't know the shape of the curve between where we are right now and when we cross that threshold, and we don't know exactly how high that threshold is that we have to get to that point. It does feel like we're getting a lot closer to that. I mean, Waymo has an existence proof for driving reasonably well in constrained circumstances, and so they're kind of the first real example that we have of a system operating in the real world, and sort of that. What Waymo has done in Chandler, Arizona, is starting to set that threshold for us. We're starting to get a sense of like where that boundary is. Once we know that boundary, it becomes easier to predict like how much farther Tesla's got to go to get to that. Personally, I'm going to be shocked if we don't get there pretty soon. And I feel like the worst case scenario is that Tesla feels like they need to do another computer upgrade to get there.
Right.
Like, they figure out how to do it and they've got the number of nines and we want 3 more nines, and we can do one of 2 things. We can either refine the neural network for 2 more years, or we can upgrade all the cars and make the computers 10 times faster, and then we can do it tomorrow, right?
Okay.
And I feel like that's the worst case scenario at this point, that sometime in the next couple of years, they look at this thing and they say, we're just not going to get the number of nines we want. We're going to upgrade the computer again.
So you just triggered 2 questions for me. One, you referenced Waymo, and I caught some controversy from Jalopnik mocked me because I said Waymo is using remote operators. And I didn't mean that remote operators are driving the car all the time. I meant what Waymo admitted to in multiple articles that I saw, that there are people who are watching the car. And if the car gets in trouble, they can take over. Is it possible to know how much of the time Waymo the software is driving the car versus the remote operator is driving the car?
Probably not. There are lots of different ways that a remote operator can contribute value to the car, and a lot of them would be completely invisible to anybody who wasn't sitting there in the center with the operator.
Yeah.
So I don't think there's any reasonable way to know what that is. And incidentally, I think having a ton of remote operators to keep an eye on their fleet. I'm a Google shareholder too, and a non-trivial part of the reason that I piled into Google when I did was because I was very excited to see them continuing to support and extend the mission that Waymo, that what's now made, which was just Google's self-driving car effort at the time, right? I believed in them then. I think what they're doing is a good thing. I think it's really unfortunate that Google is so risk averse that they're unable to overcome the technical debt that they have for the approach that they're doing right now. And yet, it could be the right thing. I mean, given the choice between having Google flip and become a Tesla copycat and having Google pursue a completely independent way of saving the problem. And frankly, for the world, it's better if Google does what they're doing, right? Because if it does turn out that there's a problem with Tesla's approach, then, or it could be that Tesla's approach is great in a particular space, and that Waymo's is complementary, right? That there's a space of things that Waymo does really well, and it would be good if the world had both of these solutions.
I should disclose that I am also a Google shareholder, and I actually consider it one of my biggest investing mistakes was that I didn't buy on the IPO. I was a Google advertiser. I was using Google AdWords when they had the IPO, and I knew how compelling it was. And I should have bought. I mean, I bought not long after the IPO. I mean, I bought at some point, and I owned Google stock. But my 2 biggest investing mistakes were not buying Google on the IPO and not buying more Amazon in 2013 when I bought Amazon. I bought Amazon, I bought it at the right time. I saw it and I recognized that I bought more than I usually would have. But if I had bought twice as much Amazon, that would have been a good move, right? So,
Amazon's been a really good investment.
The biggest lesson from those 2 experiences was when I saw Tesla and I got it, I didn't go cheap. I bought a lot. and I kept buying, and I literally have not stopped. But I mean, when I have free cash, like, what am I going to do with this free cash? I can't think of something better to do than buy Tesla. So
yeah, it's hard. Well, yeah, it's hard to come up with a better use. Yeah. I mean, there are constraints on that statement, right? But yeah. if who's going to grow 50% a year over the, who's got a 50% CAGR over the next 10 years, right? I mean, that's,
yeah. Well, we can,
there are a ton of small companies that might do it.
I want to save the business topic for another time, because I think we've been going over 3 hours. I don't know if you realize it, but so next question I wanted to ask you was, you mentioned this, and this is somewhere I was going with this. At Autonomy Day, they talked about the next generation chip. And you mentioned, like, maybe what do they need the next generation chip for? It may be that they actually don't need it at all. But I think that for the 2023 vehicle that they talked about at Battery Day, I think they will probably design that vehicle for the next generation chip. And one of the advantages of the chip will be it'll use less power. Now, I don't know. My impression is that the current generation chip already uses such low power that maybe it's not significant. But if you could use 1/3 of the electricity to make it work, then maybe that would give you an extra 10 miles of range. I don't even know how much range it gives you.
Yeah, it might.
What do you think the goals would be with the next generation chip, other than processing high resolution video and using less power?
Sparsity. I mean, they'll get more computation for less power and less cost, and there's 20 different ways they can do that. And I mean, there will eventually be another chip, right? Because that's the way the chip world works, right? The chips just keep getting better, and at some point, it's dumb to not do the upgrade. The question for Tesla right now is, when is the right time to pull the trigger on switching to the new chip? And the answer to that, I think, generally is, like, at what point is not having it a constraint to being able to do better? And I guess that's probably the only. I was gonna suggest that there's that you want to wait to upgrade the chip until you have a confidence about everything you want to put in it, right? I mean, even if it offers some benefit for you today, if there are things that you don't understand that you think you might want 3 years from now, the longer you wait, the more confident you become in exactly what you need to put in that chip, because there's a whole space of functions that could go into that chip, right? And when you push that chip out the door, you have to decide what they're going to be, what you're going to optimize the chip for. Well, the neural network space is still evolving, right? If it turns out, so the neural networks that go in right now are convolutional neural networks, right? Are you familiar with this? I tried describing it, and I did a terrible job of it, but there's an architecture called convolutional neural networks. It totally dominates the vision space right now. CNNs, convolutional neural networks, they're really good at a large space of problems. It turns out that there is another super promising architecture, which has kind of taken the world by storm over the last couple of years, which is called the transformer. It started out in language models, and in the last year or so, people have tried using transformers for solving vision problems. And transformers have demonstrated that they have certain very interesting advantages for solving vision problems. So the chip that Tesla has right now, if they wanted to run vision transformers on the chip, there are some changes they would want to make. So it might make sense for them to wait a little while and see how this vision transformer thing is working out before they spin the next chip, because they might want to prioritize putting some of that stuff in the chip. So these are the kinds of things where, if they wait a little while, the odds of them getting it right get higher. The odds of them being able to get being able to support all the approaches they might potentially want to pursue get better. So I think there's a lot of economic incentive to not do that chip until it really is going to pay off for you, right? As long as it's not hurting you, you should hold off on doing it, because it's expensive to flip the whole code base to a new chip.
Well, so maybe the theory is, my theory I was working on was you do it for the 2023 compact, the vehicle they talked about Battery Day, but maybe that's not really it. Maybe it's the humanoid robots you were talking about. Maybe we're trying to solve real world AI, and we want a general purpose chip for our robots that we're going to develop in the future rather than for the cars. Like the chips we have, they're good enough. We can do self-driving with the chips we have. We literally do not need better chips for the cars for the foreseeable future. So let's think about what else we could do with AI.
Well, there's a point where having faster hardware in the car shortens the time horizon to getting it. And I think Tesla's got plenty of good reasons to believe right now that they can get there inside the next year or two with the hardware that they have. And so there's not a lot of pressure to upgrade the hardware. Right. If a year or two from now, we're still having this conversation, it might be, we're going to go 10x up on the power because right. Like having more power is always good. Having more computational capability. Okay. Like a bigger neural network with more computational capability, you will always get better performance. The question is, at any given point in time, you have performance to make it worth the thing. But as you start running out of other options, it becomes more and more attractive as a way to like continue moving forward.
Great question here that, what's the channel? 2-Bit Da Vinci suggested this. Is there a blind spot in Tesla's camera system? Is there some like massive vulnerability because the cameras don't cover a certain spot in the right way?
In my opinion, there is not.
Okay.
I've heard this. If you look at the camera maps that Tesla has put out, I haven't sat down to figure out I could look at the video from a couple of cameras and see if there's a blind spot. It seems to me from the camera maps that they have binocular vision in every single direction except straight out the sides of the car. Like from the B pillar, if you go straight out the side of the car, you've only got monocular vision in that zone, which is directly to the side of the car. But in every other direction, as viewed from the center of mass of the vehicle, I've heard people speculate that having side view cameras mounted on the front of the car has advantage in certain situations where you're creeping out from behind an obstacle. But I certainly can understand the rationalization behind that. But I note that all existing vehicles are designed to drive by humans whose heads are right next to the B pillar, right?
Right.
So.
Right. Yeah, well, actually, I guess I would say maybe the 2023 Compact adds more cameras. The 2023 vehicle, they hinted at Battery Day. Maybe they add more cameras, and then
I suspect that they will not change the camera map for consumer vehicles. The Semi, I could imagine it using more cameras, but I could also imagine the Semi not using more cameras and working just fine without it.
All right, let me just see if I think we may be out of material unless I think I would love to have you on another time to talk about the business stuff. And I think we're past 3 hours, and honestly, I'm tired. I don't know how you're feeling.
Okay. Yeah, we should.
I don't know if you've noticed me moving around. My back is getting off and everything. So, James Douma, I want to thank you so much for coming on. Hopefully, I'll be able to persuade you to come again. I want to thank everyone else. Just remind people you can support this channel on Patreon. And there's a lot of advantage to supporting the channel on Patreon. I also got to mention the t-shirts, Elon Be Less Wrong, and the mug. If people have been seeing me drinking out this is all on the merch store. Link in the description below for elonbits.com. James, anything else you wanted to say before we're done?
Good. I had fun. Okay. Thanks for having me on.
Thank you so much.